The nearest star to us feels close enough to touch. When people hear that Proxima Centauri is only 4 light-years away, it sounds almost possible, a next-door neighbor in the cosmic neighborhood. Its small planet, Proxima B, orbits inside the habitable zone, a place where liquid water might exist. For a moment, it's easy to imagine a future probe gliding across that distant sky, sending back pictures of an alien sunrise. But behind that dream hides a truth that few like to face. In all of human history, we have not yet come close to leaving the solar system. The more we learn about the universe, the clearer it becomes that reaching Proxima B might never happen. Not for us, not for our children, perhaps not for any civilization we become. A star within reach, or so it seems. For as long as humans have looked up at the night sky, we've been drawn to the stars. They sparkle like unreachable fires, distant yet familiar, each one whispering of places beyond our world. Among them, Proxima Centauri is, by every astronomical measure, the closest star to our own Sun. Just over 4 light-years away, it sits within the same small family of stars that make up our galactic neighborhood. In cosmic terms, that's practically next door. But that phrase, nearest star, can be misleading, because even close in the language of the cosmos means something almost unimaginably far. Proxima Centauri is part of a triple star system called Alpha Centauri, and it lies about 40 trillion kilometers from Earth. 4 light-years doesn't sound like much until you remember what a light-year means. The distance light travels in 1 year, moving at about 300,000 kilometers per second. That's fast enough to circle the entire Earth 7 times in a single second. And even at that speed, it would take light 4 years to bridge the gulf between us and Proxima. For comparison, the fastest spacecraft humanity has ever built, NASA's Parker Solar Probe, travels at over 600,000 kilometers per hour. At that incredible speed, it would still take over 7,000 years to reach Proxima Centauri. That's longer than all of recorded human history. This is the first great lesson of interstellar travel. Distance is not what we imagine it to be. The scale of space breaks our sense of proportion. We are used to thinking in terms of roads, countries, even planets. But between the stars lies a kind of emptiness that defies those instincts. Our own solar system, which already feels vast, is just a tiny bubble floating in an ocean without end. Still, the dream of reaching Proxima Centauri has become one of humanity's most ambitious scientific ideas. A goal that represents both our technological courage and our deep curiosity. For decades, scientists, engineers, and visionaries have asked the same question. Could we ever send something there? Could we even once touch another star system? The answers are complicated, but the pursuit itself has already begun. Projects like Breakthrough Starshot imagine using powerful lasers on Earth to push a tiny spacecraft, no bigger than a postage stamp, to a fraction of the speed of light. If it worked, that miniature traveler could reach Proxima Centauri in just 20 years. For the first time, a human-made object might cross the vast gulf between the stars within a single lifetime. But for now, that vision is still theoretical, a blueprint for what might be possible someday. The physics are sound, but the engineering is staggering. The laser system required would have to deliver more power than any existing technology can provide. The spacecraft would have to survive collisions with microscopic dust grains at speeds that would vaporize normal materials. Even the act of slowing down near the destination, if we ever wanted to do more than just fly past, would demand new physics entirely. Every detail of the mission highlights just how extreme the challenge of interstellar travel really is. In a way, it's the scale of the difficulty that gives the dream its meaning. Standing at the edge of such impossibility reveals something about us, about our hunger to explore, even when the odds seem hopeless. It's the same impulse that once drove our ancestors to cross oceans they didn't yet understand, or to send probes into the unknown darkness beyond Pluto. Still, the phrase, "a star within reach," can feel like a trick of language. Even signals, which travel at the absolute cosmic speed limit, take 4 years just to go one way. That means if a spacecraft were to send a message home after arriving, Earth wouldn't hear from it until nearly a decade after it left, assuming it somehow got there at all. The reality is that the distances between stars are so immense that they stretch the very concepts of travel and communication to their breaking point. The scale of interstellar space forces us to confront the limits of our technology and, perhaps more importantly, the limits of our patience. The gap between stars is so wide that the fastest thing there is seems slow. When you understand that, the night sky looks different. Every star becomes a reminder of the cosmic wilderness that lies between, a silent void where distance itself becomes the greatest barrier. Proxima Centauri itself is not a grand beacon like our Sun, it's a faint red dwarf, smaller, cooler, and much dimmer. If you were somehow standing on a planet orbiting it, your sky would be painted in a dull red glow. And yet this small, quiet star has captured human attention more than most others. That's because, in a universe where everything feels so distant, even a faint spark nearby feels special. Around it, astronomers have already discovered at least one planet, Proxima B, a world that might, under certain conditions, hold liquid water. Whether it truly could support life is unknown, but just knowing it exists has changed how we see our place in the galaxy. It's a sign that other worlds, maybe even habitable ones, are not just faraway dreams. They are real, waiting just beyond the reach of our technology, but not beyond the reach of our curiosity. The invisible wall beyond the sun. Leaving the solar system sounds simple enough. Just keep going, keep flying away from the sun, and eventually you'll reach the space between the stars. But in reality, that boundary isn't marked by a line or a border you can see. There's no gate, no edge you can photograph. The true frontier of our solar system is invisible, defined not by objects, but by forces. Scientists call it the heliopause, and it represents one of the most important and least understood boundaries in all of space exploration. To understand what the heliopause is, you have to start with the sun itself. Our star is not just a glowing ball of light. It's a powerful engine that constantly spits out a stream of charged particles, a wind made of protons and electrons. This is the solar wind, and it blows outward in all directions, filling a vast bubble that surrounds everything in our system. Every planet, every asteroid, every comet you can name exists inside this invisible bubble of solar influence. The solar wind travels outward until, eventually, it meets the wind from other stars, the thin but steady gas that drifts between them. Where the force of our sun's wind finally loses its power against that interstellar gas, that's where the heliopause lies. It might seem like this boundary should be close, but it's unimaginably far away. The heliopause is more than 120 times farther from the sun than Earth is. Light from the sun takes about 8 minutes to reach Earth, but it takes over 16 hours to reach the heliopause. It's beyond Pluto, beyond the Kuiper Belt, in a region so remote that sunlight there is just a faint glow. To cross that distance is far more challenging than any journey we've ever made. Even calling it an edge can be misleading, because the heliopause isn't a fixed surface. It moves and ripples with the solar cycle. When the sun grows more active, firing off flares and storms, its wind becomes stronger, pushing the boundary outward. When the sun quiets down, the wind weakens and the heliopause drifts inward. It breathes in a sense, expanding and contracting over the course of years. The shape isn't perfectly round either. The pressure of the interstellar medium, the thin gas between stars, presses harder on one side, making the bubble uneven, like a balloon squeezed by invisible fingers. It's a living border, constantly shifting, and for a long time it existed only in theory. The first time humanity touched that invisible wall was in 2012, when NASA's Voyager 1 spacecraft, launched in 1977, finally passed through it. After 35 years of travel, the probe crossed from the sun's domain into true interstellar space. Yet even that milestone wasn't clear at first. Voyager didn't have a camera to capture the moment. There was no picture of the boundary, no glowing horizon. Instead, scientists had to read the signs hidden in data: sudden changes in charged particle counts, strange bursts of radiation, a sharp drop in solar wind. For months, there was debate about whether Voyager had really left or was just brushing against the edge. But then, a clear shift in cosmic ray intensity confirmed it. Humanity had gone beyond the heliopause. For the first time, a machine built on Earth had stepped into the space between stars. And what it found there wasn't emptiness. The region beyond the heliopause is filled with particles from other stars, cosmic rays that have been traveling for millions of years. The environment is denser than expected, and the magnetic fields twist in unpredictable ways. Voyager 1's instruments, though decades old, continued to send back clues about this mysterious realm, showing that even just outside the solar system, the universe behaves differently than we imagined. When Voyager 2 crossed the heliopause in 2018, it confirmed that the boundary isn't the same everywhere. On its side of the system, the pressure and density were higher. That told scientists that the interstellar medium isn't uniform. It's alive with fluctuations, like waves on an unseen ocean. It's humbling to realize that both Voyager spacecraft, the farthest human-made objects from Earth, are still barely past the shoreline. Even after nearly half a century of travel, they've only just stepped outside the Sun's influence. If you scaled the solar system down so that Earth and the Sun were 1 meter apart, Voyager would be less than 100 meters away, and the next star, Proxima Centauri, would be 400 kilometers farther. That comparison alone shows how vast and lonely the space beyond the heliopause really is. The heliopause is the true border between our Sun's territory and the rest of the galaxy. Inside it, everything is shaped by the solar wind. Magnetic fields, radiation, and cosmic particles all behave according to the Sun's influence. But beyond it, those same rules give way to the collective forces of the Milky Way itself. It's as if every star has its own bubble, and the space between those bubbles is the fabric of interstellar space. To cross from one bubble to another is to move from one environment of physics to another, a journey no human has ever made. That's why crossing the heliopause is a far greater leap than going from Earth to Pluto. From our planet to the outermost worlds, we're still traveling under the same star, within its protective field. Even at Pluto, the Sun's wind is still faintly pushing, and its magnetic field still shields spacecraft from much of the cosmic radiation. But beyond the heliopause, that protection fades. Spacecraft face the full harshness of interstellar particles, which can damage electronics and wear down materials at the atomic level. If we ever hope to send a crewed mission that far, we'll need shielding and communication systems unlike anything we've built before. And then there's the matter of speed. The Voyagers, traveling at over 60,000 kilometers per hour, still took decades to reach the heliopause. Future probes would need to move many times faster to explore the space beyond meaningfully. But speed creates its own dangers. At interstellar velocities, even a grain of dust becomes a deadly projectile. The space between stars is sprinkled with microscopic debris that can tear through a spacecraft moving at a fraction of light speed. This invisible minefield makes the simple act of leaving the solar system a challenge of engineering. NASA's Interstellar Probe concept envisions a spacecraft designed specifically to go beyond the heliopause, not just to cross it, but to study the space far past it. It would travel faster than any probe before, aiming to reach hundreds of astronomical units from the Sun within 50 years. Its mission would be to map the true shape of the heliosphere, measure the interstellar medium directly, and perhaps glimpse the faint glow of light from nearby stars with new eyes. But even that ambitious plan would still be confined to our neighborhood. The distance to the next star would remain so large that even the fastest probe imaginable could only inch toward it, century after century. For billions of years, every atom that made up Earth, every breath of air, every ray of sunlight existed inside the bubble of the heliosphere. When Voyager crossed that line, it became the first thing from our world to enter true galactic space. That moment may be one of the most profound in human history. It was proof that our reach, however small, can extend beyond the cradle of our star. Standing here on Earth, it's difficult to imagine what outside really means. The edge of the solar system isn't a place anyone could see or touch. It's a frontier defined by energy and motion. Somewhere out there, more than 20 billion kilometers away, Voyager 1 continues to drift through that strange environment, its faint signal still whispering home across the cosmic dark. Voyager's long goodbye. The Voyagers weren't built to reach another star. They were never meant to last this long either. When they left Earth, their planned mission was to last just 5 years, enough time to fly by Jupiter and Saturn. But their systems kept working, their power supplies held, and their instruments continued to send data long after the original goal was met. Over time, mission controllers realized that these spacecraft could do more than anyone had imagined. Each new milestone became another goodbye, first to the planets, then to the solar system itself, and finally to the Sun's influence. Their signals take more than 22 hours to reach Earth, traveling at the speed of light. When engineers send commands, it takes almost a full day to get there, and another day for the reply to return. The radio waves are incredibly faint. By the time they arrive, the signals are weaker than the energy of a snowflake hitting the ground. Yet somehow, deep space antennas on Earth can still pick them up. The Deep Space Network, a collection of massive radio dishes in California, Spain, and Australia, listens for them night and day. Each faint transmission is carefully decoded, its bits of data revealing tiny changes in temperature, magnetic fields, and cosmic radiation. Every byte matters, because every one of them comes from a place no human will likely ever visit. Even now, Voyager 1 continues to measure the strange environment of interstellar space. It senses the density of charged particles, the hum of magnetic fields, and the subtle variations in cosmic rays that drift through the galaxy. The spacecraft itself, though, is growing old. Its nuclear power source, a small plutonium generator, is slowly running out of energy. Each year, engineers have to turn off another instrument to keep the rest alive. One by one, the sensors are going dark. By the 2030s, both Voyagers will likely fall silent forever. When that happens, they'll keep flying, but without a voice. Their transmitters will fade, their instruments will cool, and their tiny onboard computers, which are less powerful than a basic digital watch today, will stop ticking. They will become cold relics, drifting through the galaxy, carrying their golden records, messages meant for anyone or anything that might one day find them. On those records are greetings in dozens of languages, images of Earth's landscapes and people and sounds of our world, the laughter of children, the chirping of birds, the rush of wind and waves. It is humanity's quiet handshake extended into eternity. Still, their slow pace doesn't make them less significant. Every kilometer they travel adds to our story of exploration. They've shown us that leaving our star's influence isn't the end of the journey. It's the beginning of a new one. For the first time, we have data from interstellar space. Voyager's measurements have changed how scientists understand the boundary of our solar system. Eventually, they'll pass near other stars. In about 40,000 years, Voyager 1 will come within 1.6 light-years of a small star called Gliese 445 in the constellation Camelopardalis. It won't be close enough to visit, but it will be the first time it passes another sun's neighborhood. Voyager 2 will follow a different path, heading toward the constellation Sagittarius. In time, both spacecraft will become like interstellar fossils, tiny objects wandering the Milky Way. A red star with a secret. If our sun is a blazing furnace, Proxima is a campfire struggling against the wind. Its light is weak and tinted red. Its warmth would barely reach any worlds that circle it. Still, in that faint glow, there might be planets. And on one of them, maybe the right mix of conditions for something more. Astronomers first confirmed Proxima's status as the Sun's closest neighbor in 1915. At first, it didn't seem special, just another dim red star among countless others. But over the years, it became something more. A symbol. If we could ever reach another star, this would be the one. The first port of call in the great ocean of interstellar space. And then, a century after its discovery, came a revelation that reignited human curiosity. In 2016, scientists using a telescope in Chile announced that they had found a planet orbiting Proxima Centauri. Proxima B was close in size to Earth and lay within the habitable zone. The announcement sent shockwaves through both science and imagination. It didn't matter that we could not go there. The idea alone was enough. For decades, the search for other worlds had been about numbers, about finding planets by the hundreds, even thousands, around distant suns. But this one felt personal. It was close enough that if you could somehow leap from star to star, this would be the first stop. Suddenly, another Earth didn't feel like an abstract concept buried in telescope data. It felt almost tangible. Still, the reality of Proxima B is far from idyllic. Red dwarf stars like Proxima Centauri are unpredictable and violent. Their surfaces boil with magnetic storms that hurl radiation into space. Proxima's flares can grow so powerful that they outshine the entire star for minutes at a time. If Earth orbited such a sun, our atmosphere would be stripped away, our oceans boiled, and our skies filled with lethal radiation. Scientists now suspect that Proxima B may endure exactly that. It orbits its star so tightly that a year there lasts just 11 Earth days. At that range, it is almost certainly locked in place, one side forever facing the star, while the other remains in endless night. The day side could be scorched by constant solar flares. The night side could be frozen and airless. Between the two, perhaps along a narrow twilight band, there might exist a region where temperatures are mild enough for liquid water, if the planet still has any at all. And yet, even with these grim conditions, no one has stopped hoping. Because if life can exist there, in that harsh, alien world, it would mean life can exist almost anywhere. Red dwarfs like Proxima are the most common stars in the universe. They make up more than 3/4 of all stars. If even one of them can support life, then the universe may be filled with it. Proxima Centauri's system might hold more than just one planet. Some studies have hinted at the presence of a second, more distant world, Proxima C, though its existence remains uncertain. It would orbit much farther from the star, making it icy and cold. But even this incomplete picture paints a small but complex solar system, one that mirrors ours in miniature form, a dim star, a possibly habitable world, and maybe another frozen one beyond. Observations show that Proxima's surface flickers constantly. Its brightness can change in just seconds. Every time telescopes point toward it, something seems to be happening. A flare, a pulse, a brief surge of light. It's a reminder that even at its faintest, a star is still alive in its own way, a boiling sphere of energy and chaos. From a distance of over 40 trillion kilometers, we can barely make out the details. Proxima Centauri appears as a single point of red light. Yet, through that tiny dot, we've detected the pull of unseen planets, measured its flares, and watched its rhythms shift. We've come to know this faint ember as if it were an old neighbor. When scientists detect a flare, they see danger. When they measure its faint light curve, they see possibility. When they refine their instruments to spot another planet, they see a reason to keep looking. And in all of it, there is that quiet, persistent hope that somewhere near that red glow, something else might be looking back. The illusion of the habitable zone. When scientists announced that Proxima B lay within its star's habitable zone, the phrase spread quickly. News headlines called it an Earth-like world. Some even hinted it could host life. The words themselves, habitable zone, sound full of promise. They suggest a place where oceans might shimmer, where skies might glow, where something could breathe. But this is one of science's most misunderstood ideas. The habitable zone does not mean a planet is actually habitable. It only means that, in theory, if a planet had the right atmosphere and the right pressure, liquid water could exist on its surface. It is a guess based on distance, not on reality. It says nothing about what the planet is truly like, whether it has air, oceans, or even solid ground. It is a thin line drawn on a map of the universe, telling us where life might survive, not where it actually does. For Proxima B, that line is more illusion than promise. The planet orbits very close to its red dwarf star. If it were orbiting a sun like ours, it would be scorched beyond recognition. But Proxima Centauri's faint glow makes that tight orbit just barely warm enough for water, in theory. Red dwarfs are unstable stars, and Proxima Centauri is one of the most active of them all. Its flares are thousands of times stronger than those our Sun produces, and they happen regularly. If Proxima B ever had an atmosphere, it may no longer exist. Without that protective layer, water cannot stay liquid. It either freezes solid or evaporates into space. And if there is no water, the idea of habitability disappears entirely. The habitable zone becomes a hollow term, a mathematical circle drawn around a dangerous star. Astronomers know this, of course. When they talk about habitability, they use the term carefully as a first clue, not a conclusion. But outside the world of research, the word takes on a life of its own. It feeds human imagination. It's easier to picture an ocean world than to think of a scorched, airless rock. The phrase habitable zone offers a small comfort, a sense that life could be common, that Earth is not alone. But science often hides beneath layers of hope and simplicity. The problem is that habitable is far more complex than distance. For a planet to truly support life as we know it, a long list of conditions must line up perfectly. It needs water, but also an atmosphere thick enough to trap heat. It must have protection from radiation, likely through a magnetic field generated by a molten core. Its orbit must be stable, avoiding wild swings in temperature. Its rotation must keep the climate balanced, not leaving one side in endless night. And perhaps most importantly, it must remain stable for billions of years, long enough for life to begin, evolve, and endure. We can estimate some of these factors from afar, but most remain unknown. When we detect a planet like Proxima B, what we really find is a shadow, a dim signature in starlight that tells us it exists and roughly how massive it is. We don't yet know what it looks like, what it's made of, or whether it even has an atmosphere. For all we know, it could be a barren rock like Mercury or a frozen world like Pluto. Even within our own solar system, the idea of a habitable zone is misleading. Venus, for example, sits inside the Sun's habitable zone, close enough that liquid water should be possible. Yet its surface is a hellish wasteland, hot enough to melt lead, wrapped in a choking atmosphere of carbon dioxide and sulfuric acid clouds. The pressure there would crush a spacecraft within minutes. Earth and Venus are neighbors, nearly the same size, yet one teems with life and the other burns under a toxic sky. The habitable zone alone cannot explain that. Mars too challenges the concept. It lies near the edge of the Sun's habitable zone and may once have had rivers, lakes, and oceans. Today it's a frozen desert, its thin atmosphere unable to hold warmth. Water still exists there, locked as ice beneath the surface, but the planet is far from alive. The lesson is clear. Being in the right place does not guarantee the right conditions. In a way, the habitable zone is like a mirage in the desert, a sign that water could be nearby, but not proof that it is. It helps scientists narrow their search to know where to look more closely. But what we find when we look often breaks the illusion. Proxima B's case is even more uncertain because of its star's nature. Red dwarfs burn slowly, sometimes lasting trillions of years, but their youth is chaotic. If life ever does arise around such stars, it must either evolve extreme protection or begin long after the star quiets down, which could take billions of years. We do not yet know if that's possible. Still, the idea that life could exist around red dwarfs remains enticing. Because these stars are so common, their habitable zones, no matter how unstable, represent countless possible worlds. Even if only 1 in a million manages to hold on to its atmosphere, the universe would still have billions of potentially life-bearing planets. When telescopes like the James Webb Space Telescope, or JWST, point towards systems like Proxima Centauri, they're not looking for oceans or forests. They're looking for signs of air, traces of molecules like oxygen, methane, or carbon dioxide that might reveal the planet's chemistry. A single spectral line in the starlight could suggest the presence of an atmosphere. From that, scientists can guess whether water might still exist. It's detective work on a cosmic scale, using light itself as the only witness. And yet, even if Webb or future telescopes detect something that looks like an atmosphere, we will still not know if the planet is truly habitable. It could have clouds of hydrogen instead of oxygen, or be smothered in thick smog. It could be a world of steaming acid or endless ice. From 4 light years away, our view is a whisper, not a picture. Perhaps the word habitable tells us more about ourselves than about other worlds. It reflects our longing for familiarity. We imagine other planets with blue skies, rocky ground, and gentle sunlight, because those are the conditions that gave rise to us. But life might not need any of those things. It could exist in ways we can barely imagine, beneath ice, inside rocks, or floating in clouds. Our definition of habitability may be too narrow, shaped by one world and one experience. Still, the term remains useful because it gives us a starting point. It's a map drawn by our current understanding, marking where the odds might be a little better. It doesn't promise life, but it keeps us searching. Our fastest ships are still drifting. When a probe travels to Mars, we wait a few months for it to arrive. A trip to Jupiter might take several years. That feels reasonable. We can count those years, plan around them, and even live to see the results. But when we talk about tens of thousands of years, we leave the realm of human experience entirely. A journey to Proxima Centauri with today's technology would not just outlast a civilization, it would outlast multiple ones. Empires would rise and fall, languages would evolve and vanish. Continents would shift under ice and sea, all while the probe continued to drift through the dark, still not halfway there. A probe like Voyager shows how small a human lifetime really is. The spacecraft's radio signal takes more than 22 hours to reach Earth. Every message sent from Voyager today is a whisper from yesterday, already old by the time it arrives. When we listen to Voyager's signal, we are listening to a machine speaking from the past. At Voyager's speed, it travels about 500 million kilometers per year, a number that sounds impressive until you realize that a single light year is almost 10 trillion kilometers. That means Voyager 1, despite its decades of travel, has covered less than 1/500th of a light year since it left Earth. The Voyagers, the Parker Solar Probe, New Horizons, they are like drifting seeds, each carrying a fragment of our curiosity into the endless dark. Long after every mission controller, every engineer, and every observer on Earth has passed away, those probes will still be moving outward, carrying with them the memory that someone once wanted to see what lay beyond. It's tempting to think that future technology will change everything, that one day we'll leap from thousands of years to just decades. Concepts like nuclear pulse propulsion, fusion drives, or even laser sails are often imagined as solutions to this problem. But even those ideas, as bold as they are, face enormous challenges. They require energy sources that don't yet exist, materials that can withstand unimaginable stress and precision that borders on impossible. If one of them worked perfectly, if we could accelerate a probe to 1/10 the speed of light, the trip to Proxima Centauri would still take more than 40 years. That's a human lifetime. That's the scale of the challenge. Our fastest ships today are crawling compared to what's needed. They're heroic, but tiny against the backdrop of cosmic distance. To reach even the nearest star, we would have to push beyond everything we know about propulsion, power, and patience. For now, our voyages remain symbolic, gestures of exploration, not journeys to destinations. The hard ceiling of rocket physics. Every rocket that has ever left Earth, from the first primitive test flights to the mighty Saturn V that carried humans to the moon, has been powered by the same basic idea: burning fuel. The principle is simple enough that even a child can understand it. A rocket throws mass out one end, and by doing so, it moves in the opposite direction. This is Newton's third law, the rule that every action creates an equal and opposite reaction. It is elegant, reliable, and has taken us farther than any other form of propulsion ever invented. But it also comes with a hard ceiling, a limit that no amount of engineering genius can truly break. The problem lies in the numbers that govern how rockets work, the mathematics of thrust, mass, and fuel. A chemical rocket carries everything it needs to move, its fuel and its oxidizer. It can't refill in space or draw power from the vacuum. To go faster, it must burn more fuel. But the more fuel you add, the heavier the rocket becomes, which in turn requires even more fuel to lift that extra mass. It's a vicious circle, one that punishes ambition. Every extra kilogram of propellant adds to the total weight, which means you get smaller and smaller returns from each improvement. This relationship is described by something called the rocket equation, first written down in the 19th century by Konstantin Tsiolkovsky. It tells us how much speed a rocket can gain based on the amount of fuel it carries and the speed at which that fuel is expelled. What engineers call the exhaust velocity. For chemical rockets, the exhaust velocity is limited by the energy released in chemical reactions, and those reactions are well understood. Hydrogen and oxygen, when burned together, produce some of the highest energies known in chemistry. The result is a maximum exhaust velocity of around 4.5 kilometers per second. That's impressive, but it's a ceiling built into the laws of chemistry. No matter how clever the design, you can't squeeze more energy out of those atoms than nature allows. To escape Earth's gravity, a spacecraft must reach at least 11 kilometers per second, more than twice what chemical combustion can directly produce. Rockets achieve this by staging, throwing away empty fuel tanks to shed mass as they climb. The Saturn V, for example, used 3 stages, each smaller and lighter than the last, to reach orbit and beyond. But this technique doesn't change the underlying math, it only stretches it. No matter how many stages you add or how light you make the structure, the energy limits of chemical reactions stay the same. Once a rocket has used its fuel, it's coasting forever at whatever speed it achieved. That's why the fastest spacecraft humanity has ever launched, even those using the most efficient designs, all top out in roughly the same range, tens of kilometers per second. Pushing past that requires exponentially more energy. Doubling a rocket's speed doesn't mean doubling its fuel. It means multiplying it many times over. In fact, to double your speed, you might need not twice as much fuel, but 10 or 20 times more. It's like trying to climb an endlessly steepening hill. Each step forward demands more strength than the last, until eventually you can't move at all. Even the mighty Saturn V, which carried the Apollo astronauts to the moon, was mostly fuel. More than 90% of its total mass at launch, some 2,700 tons of propellant, was consumed just to push a small capsule and a handful of people beyond Earth's pull. What reached space was only a fraction of what began the journey. The same is true for every rocket ever built. The payload, the thing you actually want to deliver, is always the smallest part of the whole. This imbalance is what keeps us grounded near home. Rockets can take us to orbit, to the moon, to Mars perhaps, but the stars are something else entirely. Imagine trying to build a chemical rocket large enough to reach even 1/10 the speed of light. The amount of fuel required would be beyond absurd, more mass than exists in our entire planet. The rocket equation makes it clear. The faster you want to go, the worse the math becomes. It's not just impractical, it's physically impossible with chemistry. At some point, adding more fuel adds nothing but weight. The rocket collapses under its own burden. That's why space agencies and physicists often talk about propulsion ceilings. Chemical rockets are already near theirs. Every new design, whether it's the Space Launch System, Vulcan Heavy or Starship, uses variations of the same old idea. Controlled explosions, pushing exhaust downward. Technological developments may have made them more reusable, cheaper or safer, but in terms of speed, they are bound by the same chemistry that powered the early rockets of the 20th century. The improvements are mostly logistical, not fundamental. We are brushing against the top of what this method can do. It's humbling to realize how narrow that limit is compared to the scale of space itself. Chemical rockets can get us from Earth to the Moon in a few days, to Mars in several months, and to the outer planets in years. But after that, their usefulness fades quickly. Beyond the orbit of Neptune, their tiny reserves of thrust can barely make a difference. Spacecraft like Voyager and New Horizons rely mostly on gravitational assists, slingshots around planets, to gain the extra speed they need. Even that trick only helps so much. Once they've left the solar system, they're coasting forever, slowly bleeding energy into the dark. The reason for this inefficiency lies in how energy is stored and released. In chemical rockets, energy comes from rearranging the bonds between atoms, but those bonds hold only a limited amount of power. Nuclear reactions, by comparison, release millions of times more energy per unit of mass. That's why the next generation of theoretical propulsion, fusion or fission, is seen as the only real way forward. But even those methods come with immense technical challenges. For now, chemistry remains our workhorse, a technology both familiar and frustratingly weak. And even if we could push a chemical rocket harder, we'd quickly hit another wall. Heat. The faster fuel is burned, the hotter the engine becomes. At some point, no material can survive the temperature. Even advanced alloys melt, vaporize, or crack under the stress. Engineers can design cooling systems, but those systems add mass, which in turn demands more fuel, which adds more heat. It's an endless cycle of trade-offs, one that ends always at the same barrier. This is the hard ceiling of rocket physics. Every form of propulsion depends on the energy locked inside matter, and chemical energy simply isn't enough. The speeds required to cross interstellar distances are so vast that our rockets are like candles trying to light the night sky. They glow for a moment, burn through their fuel and fade. When the first astronauts climbed into their capsules, they were sitting atop machines that represented the absolute peak of what chemistry could achieve. 60 years later, despite enormous advances in materials, computing, and design, we still rely on the same process. There's something both heroic and tragic about that. Heroic, because we've reached incredible heights with limited tools. Tragic, because those tools have taken us as far as they can go. The dream of fusion drives. The idea of a fusion drive was born from the same human instinct that led to rockets, the desire to turn the deepest forces of nature into motion. If fire could lift us off Earth, maybe the power that fuels the stars themselves could carry us across the void. Fusion is what lights the sun. It's the process that turns hydrogen into helium, releasing enormous energy in the process. A fusion engine would do the same, but under control, capturing that power and turning it into thrust. In theory, it could make interstellar travel possible within a human lifetime. In practice, it remains a dream locked behind walls of physics and engineering we have not yet learned to climb. The idea first gained serious attention in the 1970s with a project known as Daedalus. It was a study by the British Interplanetary Society. Could humans, using the technology they expected to have within a century, build a spacecraft that could reach another star? The team chose Barnard's star, a red dwarf about 6 light-years away, as the target. The goal was not to send people, but a probe, something that could cross that unimaginable distance within 50 years. Project Daedalus imagined a ship nearly 200 meters long, powered by nuclear fusion. The engines would burn pellets of deuterium and helium-3, small isotopes of hydrogen that release enormous amounts of energy when fused. To ignite them, the ship would use powerful electron beams, triggering miniature thermonuclear explosions inside a magnetic chamber. Each tiny blast would push against a massive magnetic nozzle, creating thrust. Over 4 years, the ship would accelerate to 12% of the speed of light, more than 36,000 kilometers per second, fast enough to cross interstellar space in half a century. The numbers were staggering. To fuel such a journey, the spacecraft would need around 50,000 tons of fusion fuel, all of it mined from the atmospheres of gas giants like Jupiter. It would be assembled in orbit, far from Earth, because no planet could safely host a rocket that detonated small nuclear explosions as its engine. The cost and complexity were beyond anything possible then, or even now. But the physics was sound. In principle, a fusion engine could work. The challenge was not in the math, but in building something that could survive its own power. That is where the dream has remained stuck ever since. Fusion itself is hard. Containing it is harder. For decades, scientists on Earth have tried to recreate the sun's process inside reactors, not to fly ships, but to produce electricity. They have built magnetic machines like the tokamak and stellarator, which hold plasma in place using immense magnetic fields. They have used lasers to compress tiny fuel pellets in labs like the National Ignition Facility. The progress is real, but painfully slow. Reaching ignition, the point where fusion releases more energy than it consumes, has been achieved only for fractions of a second and under delicate lab conditions. Turning that into something steady, controlled and powerful enough for propulsion is another leap entirely. A fusion drive would need not just to create fusion, but to do it thousands of times per second, in perfect rhythm, while surviving the heat and radiation of its own exhaust. The chamber walls would be bombarded by energetic particles hotter than the sun's core. The magnetic fields needed to contain the plasma would have to be stable and precise. Any tiny disturbance could destroy the entire system. And all of this would have to happen inside a spacecraft light enough to accelerate to a significant fraction of light speed. It's not impossible in theory, but in practice, it's a mountain of challenges stacked one atop another. Yet, fusion stays in the imagination as humanity's next big step. Modern versions of Daedalus have been proposed, most notably Project Icarus in the 2010 S, a collaborative effort of engineers and physicists revisiting the concept with modern tools. The goal is the same: to design a self-sustaining fusion-powered probe that could reach another star within a century. Icarus adds refinements, better magnetic confinement, lighter materials, smarter onboard computers, but the scale remains enormous. The challenge isn't just in building it, it's in sustaining its operation over decades without maintenance, while traveling through interstellar dust that could erode its hull grain by grain. What makes fusion so alluring is the energy density. A fusion reaction releases millions of times more energy per kilogram than chemical fuel. With that kind of power, a spacecraft could accelerate for months or years instead of minutes. It could keep pushing until it reached a significant fraction of the speed of light. A journey to Proxima Centauri could take only a few decades. That's fast enough to imagine a ship launched by one generation and reached by the next. It's still slow in cosmic terms, but it would bring the stars within the edge of human patience. But the beauty of the idea hides its fragility. The fusion process itself demands precision that no spacecraft has ever needed to maintain. Even our most advanced reactors on Earth are enormous, fragile machines that depend on teams of scientists and constant calibration. A fusion drive would need to operate autonomously in deep space for decades, handling immense forces without repair. It would need to store and feed thousands of tons of fuel pellets into its chamber with perfect timing, while surviving micrometeorite impacts and radiation. It's not just a question of making fusion work. It's making it work in the harshest environment imaginable. Still, research continues in small ways. Advances in superconductors and magnetic field design have made compact reactors more plausible. Some labs are exploring new approaches, like magnetized target fusion, which blends the principles of inertial and magnetic confinement. These concepts, if miniaturized, might one day serve as the foundation for a fusion engine. Others dream of hybrid systems, where lasers ignite micropulses of fusion and each pulse propels the ship forward like a controlled explosion. It's speculative science, but not without merit. The same tools that could one day power cities might also power ships to the stars. Yet it's important to remember that no fusion device has yet produced continuous power, even on Earth. What we can do in a lab for a few seconds, we are still decades away from sustaining. Turning that into propulsion, something that must work for years, pushes that timeline even further. The dream of fusion drives belongs to the border between engineering and imagination. It's a picture of what might be possible if humanity solves some of its hardest scientific problems. But for now, it remains an idea more than a plan. Every generation has had its unreachable dream, and fusion is ours. It sits at the horizon of our technology, always just out of reach, yet bright enough to keep us moving toward it, beaming a ship across the stars. Imagine a spacecraft with no engine, no fuel, and no crew. Just a thin, shining sail pushed by light itself. Instead of carrying its own propulsion system, the spacecraft would ride on energy projected from home, propelled by the steady pressure of light. It sounds like science fiction, and in many ways it still is, but the physics behind it is real. This is the vision of Breakthrough Starshot, an attempt to turn light, the most constant traveler in the universe, into a means of flight. The concept begins with a simple truth. Light carries momentum. Even though photons have no mass, they still exert a tiny push when they strike something reflective. On Earth, this force is far too weak to move anything noticeable. But in space, where there's no air resistance, even the faintest pressure can build up speed over time. If you reflect a constant stream of light onto a mirror, it will eventually accelerate. Scientists have dreamed of using sunlight this way for decades. The idea of a solar sail, pushed by photons from the sun, has appeared in literature, films, and real missions like Japan's Icaros and NASA's NEA Scout. But sunlight is weak. It fades quickly with distance. To go to another star, you'd need something stronger, an artificial sun made of lasers. That's where Breakthrough Starshot comes in. Announced in 2016 and backed by physicist Stephen Hawking and investor Yuri Milner, the project proposes building a vast array of ground-based lasers, possibly thousands of them working in perfect synchronization, to create a beam of unprecedented power. This beam would focus on a tiny spacecraft attached to a reflective sail, only a few meters wide, but weighing just a few grams. The goal is to accelerate that sail to 20% of the speed of light, about 60,000 kilometers per second, in just a few minutes. At that speed, it could reach Proxima Centauri in a little over 20 years. It's hard to overstate how radical this idea is. Traditional spacecraft are heavy, filled with fuel and instruments. Starshot flips that logic entirely. The probe would be no bigger than a microchip, carrying miniature cameras, sensors, and communication systems. The sail would be a thin, ultra-reflective sheet made of advanced materials like graphene or metamaterials, something light enough to survive the heat of the laser and smooth enough to remain stable under extreme acceleration. In a sense, the ship wouldn't fly under its own power. It would be thrown across space by Earth's light. Once the beam turned off, it would coast for decades through the dark, carrying humanity's presence into another star system. But the simplicity of the concept hides enormous difficulty. The first and most obvious challenge is focus. To accelerate a sail to a fraction of light speed, the laser must remain perfectly aligned with it for the entire boost phase, several minutes, while the sail races thousands of kilometers away from Earth. Any wobble or misalignment would cause the beam to miss or burn through the sail. At those speeds, even a tiny variation in the reflective surface could cause it to spin out of control. The engineering precision required is beyond anything humanity has ever attempted. The array would need to coordinate its thousands of lasers with millisecond timing, adjusting for atmospheric distortion, Earth's rotation, and thermal expansion. Then there's the problem of energy. To reach 20% of light speed, the laser array would need to output around 100 gigawatts of power, roughly the entire electrical capacity of a large country, for several minutes straight. That's an extraordinary burst of energy, and it must be concentrated into a beam that travels through the atmosphere without scattering. Even building such an array poses a staggering challenge. It would need to cover several square kilometers and operate with perfect synchronization. And once the sail leaves the beam, it's gone forever. There's no slowing down, no way to turn, no return trip. Assuming those obstacles are somehow overcome, the journey itself remains dangerous. Even a grain of dust no bigger than a speck of sand could release enough energy to vaporize the spacecraft on impact. Engineers have proposed ways to protect it, using forward shields or perhaps orienting the sail edge-on during flight, but there's no proven solution yet. Every kilometer traveled through interstellar space would be a silent gamble against the unknown. Communication is another major hurdle. A probe only a few grams in weight can't carry a large antenna or powerful transmitter. When it finally reaches Proxima Centauri, 4.2 light-years away, its signal would take over 4 years to return to Earth, and would be so faint that even our largest radio telescopes might struggle to detect it. Engineers imagined the sail itself doubling as a transmitter, beaming data back using a tiny onboard laser, but that requires pinpoint aiming across trillions of kilometers. The challenge is not only to reach the stars, but to whisper back from them. Despite all these difficulties, the appeal of the concept is undeniable. It represents a new way of thinking, one that doesn't rely on carrying fuel, but on external power projected from home. If perfected, the same method could be used for slower, larger probes to the outer planets, or even for sending small payloads to distant corners of the solar system at record speed. It's an approach that could, over time, transform exploration from rare and expensive missions into something more like a network. Tiny, mass-produced scouts riding beams of light to map the universe. In a way, breakthrough Starshot is as much a philosophy as it is a technology. It accepts the limits of rockets and embraces something entirely different, the idea of separating the energy source from the spacecraft. Instead of carrying the burden of power with us, we send it after. That's what makes the concept so elegant. It turns space travel into something more like wireless energy transfer on a cosmic scale. The ship becomes featherlight, the Earth becomes the engine. But there's also fragility in that vision. The entire system depends on a single connection, the beam between the lasers and the sail. If that connection breaks, the mission fails. Once the beam fades, the probe becomes a drifting speck, unpowered and unprotected, forever coasting through darkness. It's a reminder that even our most advanced ideas are still bound by the reality of physics and distance. The further we dream, the more fragile our reach becomes. And yet, the idea that a human-made object, no larger than a thumbnail, could cross the gap between stars is a symbol of both our limits and our courage. It says something profound about how far we're willing to push the possible. The first Starshot probe, if it's ever launched, may not survive the journey. It may be vaporized by dust, or its signal may never reach us. But the attempt itself would mark a turning point. For now, the technology is still on drawing boards and computer simulations. But if it ever works, it would mean that humanity has found a way to touch another star without moving a single atom of fuel. When atoms become the enemy, space looks empty, but it isn't. Between the stars stretches a thin haze of matter, hydrogen atoms, microscopic dust, and occasional clusters of heavier elements drifting like invisible ghosts. It's so sparse that, on average, only a few atoms occupy each cubic centimeter. To human senses, it would seem like nothing at all, but when you move fast enough, even nothing can become deadly. For a ship traveling near the speed of light, those scattered atoms turn into a storm of bullets. When something moves close to light speed, its kinetic energy rises dramatically. Even a tiny object can carry immense force. A single hydrogen atom, striking a spacecraft at 1/10 the speed of light, hits with the energy of hard radiation. Multiply that by billions upon billions, and the emptiness between stars becomes a barrage of invisible fire. The faster a ship goes, the worse it gets. At 10% of light speed, the impact of a dust grain no larger than a sand particle could release as much energy as a small explosive. At half the speed of light, it would be like being hit by a bullet, moving faster than anything on Earth. At 99%, a speck of dust could tear through metal like a cannon shell. For a starship, this turns interstellar space into something like flying through a minefield. The atoms are too small to see or avoid, and they move relative to the ship at incredible speeds. Even the thinnest parts of interstellar gas, which are harmless to slower spacecraft, become plasma waves capable of stripping atoms off the hull. The faster you go, the denser the medium appears, not because there are more atoms, but because of how relativity compresses the particles ahead of you. The ship would experience them as a fierce, continuous wind, a radiation storm of matter itself. To survive such a journey, any interstellar craft would need to become a fortress. Engineers who study hypothetical relativistic flight imagine ships with immense shielding at the front, made of thick layers of material designed to absorb or deflect the impacts. The bow might be shaped like a long cone, spreading energy away from the main structure. Some designs even propose magnetic fields powerful enough to push charged particles aside before they strike. But each of these solutions brings new problems. The shields would add weight, and every extra kilogram makes acceleration harder. The magnetic fields would need enormous energy, and they might not stop neutral atoms or dust grains. Every form of protection adds another challenge. The paradox is cruel. To make the trip short, a ship must go fast. To survive going fast, it must carry protection that makes it heavy, which slows it down again. There's no simple balance point. The faster you try to go, the more the universe itself fights back. Even if you imagine perfect shielding, something that could absorb or vaporize dust on impact, the heat alone would be catastrophic. The constant rain of particles at near light speed would generate immense friction, building up energy faster than any cooling system could handle. The front of the ship could glow white hot, even in the frozen dark of interstellar space. Scientists have tried to estimate what this would mean in practice. For example, a ship traveling at just 30% of the speed of light would encounter about 1 trillion particles per square meter every second. Each particle might carry only a tiny fraction of a joule, but together they would deposit immense amounts of energy. The constant bombardment would slowly erode the hull, creating radiation that could fry electronics or damage onboard systems. Over time, even the most advanced materials could crumble. The faster the ship goes, the more violent the environment becomes, until the void itself turns lethal. It's easy to forget how hostile interstellar space is, because we imagine it as endless emptiness. But the emptiness hides energy. It hides radiation from distant stars, cosmic rays traveling for millions of years, and dust grains left behind by dying suns. Every one of those particles, harmless to a stationary observer, becomes a weapon when hit at relativistic speed. It's like driving through a fine mist that turns to steel needles the moment you accelerate. One possible solution, at least in theory, would be to travel slower. If you limit the ship to just a few % of the speed of light, the impacts become less catastrophic. But that also means the journey takes longer, centuries, even millennia. A mission to Proxima Centauri at 1% of light speed would take over 400 years. The probes we launch now would be long dead by then. Humans, if they ever rode such a vessel, would never live to see its destination. And so we find ourselves caught between speed and survival. Go too fast and the ship is destroyed. Go too slow and the mission loses all meaning. The universe, it seems, guards its distances with invisible walls. There's also the problem of cosmic rays. Even today, astronauts aboard the International Space Station experience doses of cosmic radiation hundreds of times higher than on Earth's surface. For a ship moving at a significant fraction of light speed, those rays would appear even more intense due to relativistic effects. The forward direction of travel would compress the incoming radiation into a narrow, deadly beam. The ship would essentially be flying into a constant storm of hard radiation, enough to damage electronics and, if crewed, to kill its passengers without extraordinary shielding. Some have suggested using the very atoms ahead as part of the solution, creating a magnetic bow wave that ionizes the incoming gas before it hits, deflecting it sideways. It's an elegant idea, but it requires fields far stronger than anything we can generate. The ship would need superconducting magnets the size of buildings, cooled to near absolute zero, operating flawlessly for decades. Even then, neutral dust grains would remain a problem. The truth is that we've only begun to understand how complex this problem really is. The interstellar medium isn't uniform. It's filled with patches of denser gas, shock fronts from old supernovae, and clouds of dust hundreds of light years wide. A ship could pass through regions of relative safety, then suddenly enter a zone thick with microscopic debris. Each grain it strikes would erode its surface a little more. Over decades, that erosion could eat through meters of shielding. What's most unsettling is how invisible the threat is. You can't see a hydrogen atom coming. You can't chart every dust grain between here and Proxima Centauri. The interstellar medium is too vast, too thin, too random. Even if you could map it, the ship itself would be moving too fast to react in time. There would be no dodging, no shielding strong enough to last forever. The journey would depend entirely on how well we could guess what lies ahead, and how well our materials could endure what they cannot avoid. Navigating through nothing. Once a spacecraft leaves the solar system, it leaves behind the last familiar lights of home. The sun, the planets, the soft pull of our magnetic field. Beyond that boundary, there are no guideposts, no landmarks, and no compass that works. A ship moving between the stars must navigate through pure darkness, surrounded by endless points of light that all seem equally far away. It's a journey through nothing, where even a fraction of a degree's error can mean drifting off course forever. On Earth, navigation is simple because we have stable reference points. We can follow coastlines, track stars, or use magnetic compasses to orient ourselves. Even in near-Earth space, satellites rely on the Sun and Earth's magnetic field for positioning. But as a spacecraft travels outward, those tools fade. The Sun becomes a faint star among billions. Its gravity weakens, its light grows dim, and its magnetic field dissolves into background noise. The familiar grid that has guided every spacecraft so far simply disappears. What's left is an ocean of emptiness, and finding direction within it becomes one of the hardest problems in interstellar flight. A ship leaving the solar system would need to rely entirely on the stars themselves. This is not new. Ancient sailors once used constellations to navigate across Earth's oceans. But for a starship, the challenge is magnified to the extreme. The stars it sees are not fixed. They move slowly over time, and their apparent positions change as the ship itself moves at high speed. Light from those stars takes years to reach the ship, meaning its map of the sky is already out of date. The faster it travels, the less accurate its picture becomes. Even the most advanced navigation system must constantly update its sense of the cosmos, and it must do so without any outside help. One proposed method involves pulsars, rapidly spinning neutron stars that emit beams of radio waves in precise repeating patterns. Each pulsar has a unique rhythm, like a cosmic clock. By measuring the arrival times of signals from several known pulsars, a spacecraft could triangulate its position, much like how GPS works on Earth. This technique, known as XNav or X-ray navigation, has already been tested in orbit around Earth with promising results. In theory, a network of pulsars could serve as a natural interstellar GPS, giving a ship coordinates based on the timing of their flashes. But even this elegant system faces limits. The signals are faint and easily drowned out by noise. The detectors must be extremely sensitive, cooled and shielded from interference. A ship traveling at relativistic speeds would also have to account for time dilation, the strange warping of time that comes with moving near the speed of light, which would shift the timing of those pulses and make calculations far more complex. If pulsars can provide position, the next question is orientation, knowing which way the ship is pointed. In deep space, a spacecraft's attitude or rotation can't be measured against any nearby object. There's no up or down, no horizon. Engineers must rely on gyroscopes and star trackers, instruments that sense rotation and compare observed star patterns to a stored map. But these systems drift over time. A gyroscope, no matter how precise, will accumulate tiny errors. Over months or years, those errors grow until the ship's computer no longer knows which way it's facing. On interstellar timescales, even a 1-degree mistake could send a probe veering thousands of kilometers off target. Correcting that drift would require continuous recalibration, comparing the apparent positions of distant stars and galaxies to what the ship expects to see, a task requiring perfect timing and computational precision. Communication makes this even more delicate. To talk to Earth, a spacecraft must point its antenna exactly toward home. A radio dish, just a few meters wide, sitting billions of kilometers away, has to be aligned with incredible precision. If the beam drifts even slightly, the signal misses Earth completely. And as distance grows, the target shrinks. For interstellar missions, this means even tiny course corrections must be made carefully, using thrusters that produce almost no unwanted rotation or wobble. Every pulse of a maneuvering jet must be planned, modeled, and verified before being fired. A mistake made at 1% of light speed could never be undone. Without the sun's gravity to anchor it, a spacecraft in interstellar space also faces another invisible threat: drift. Space is not perfectly smooth. It contains faint gravitational tides from nearby stars and clouds of gas. Over long timescales, these tiny forces can nudge a ship's trajectory, changing its path by subtle degrees. If a probe were aimed precisely at another star, those small tugs could bend its flight enough to miss the target entirely. Correcting for this requires a continuous awareness of position, but the farther a ship travels, the harder it is to measure that position accurately. By the time Earth receives a signal saying the ship is slightly off course, the ship will already be light years farther along. That's why interstellar navigation demands autonomy. A probe cannot wait for instructions from home. Light-speed communication is simply too slow. By the time engineers on Earth could react to a problem, the mission would already be lost. The spacecraft must be able to sense, think, and adjust by itself. It must carry a model of the galaxy, measure its motion, and correct its flight path without human help. That kind of intelligence requires software capable of interpreting starlight, timing pulses, and running constant self-checks, all while surviving cosmic radiation and decades of isolation. Some engineers imagine ships equipped with small optical telescopes, scanning the sky continuously. The onboard computer could compare the observed star field to known catalogues, like a sailor checking the stars against a map. By calculating the subtle parallax shifts, how stars appear to move relative to each other as the ship changes position, it could estimate its speed and direction. But those shifts are tiny. Even for a ship traveling a tenth of the speed of light, it might take years before any measurable change in the star field appears. During that time, the ship would have to trust its instruments completely, adjusting its path based on predictions and simulations rather than clear measurements. The same difficulty applies to turning or decelerating. A ship that travels light years must plan its movements long in advance. Every change in orientation, every correction burn, uses precious energy and alters the geometry of the onboard navigation system. Thrusters designed for stability must fire symmetrically or the ship could start to spin. Without external reference, detecting and stopping that spin becomes nearly impossible. The craft would have to sense the stars sliding across its cameras and calculate the motion backward. A kind of celestial dead reckoning that depends entirely on how well its instruments age. In human terms, this is like sailing across an ocean so wide that the stars above are your only compass. Except the stars themselves are moving. The ocean is invisible, and every gust of cosmic wind might change your heading. There is no visual horizon to correct against, no sense of speed, no resistance. The ship could be drifting off course for years before it even realizes it. To stay aligned with the target star, the navigation system must maintain accuracy down to fractions of a microdegree, something no existing spacecraft has ever achieved over such timescales. Even the simple act of measuring time becomes difficult. Atomic clocks on board must remain stable for decades or more, unaffected by radiation or temperature shifts. A single timing error could throw off pulsar calculations, leading to navigational drift. Engineers talk about needing self-healing systems, networks of redundant clocks and sensors that constantly check each other, detecting flaws before they grow catastrophic. The craft must not only know where it is, but know that it knows, a strange kind of recursive awareness that might one day define the first intelligent probes. Then there's communication itself. The Deep Space Network already operates at the limits of sensitivity. Engineers imagine using laser communication instead, focusing a narrow beam of light directly at Earth. But this makes alignment even more critical. The laser must stay locked on its target with near-perfect accuracy, despite the ship's constant motion and vibration. Navigating through nothing, then, is not simply a technical challenge. It asks how we find our way when there are no markers left to guide us, when even light and time become unreliable companions. A ship that travels between the stars must do more than move. It must perceive. It must turn the emptiness itself into a reference, reading the faint whispers of radiation and gravity as clues to its position. The deceleration problem. Getting a spacecraft up to incredible speed is only half the battle. The harder part, the part that's often quietly left out of grand interstellar mission concepts, is slowing down again. Once a probe is racing between the stars, it has nothing to push against, no air to break through, no planet to orbit until the journey is over. It will keep moving forever unless something stops it. In the deep vacuum of space, motion is eternal. That's what makes the deceleration problem so difficult. If a probe were launched toward Proxima Centauri and somehow accelerated to a fraction of light speed, it would not be able to slow down. With no external braking force and no fuel to burn, it would shoot straight past the system, vanishing into the darkness beyond. The faster it travels, the worse the problem becomes. At 10% of light speed, the probe would cross the entire Proxima system in just a few hours. It could gather data as it flew by, but never stop to take a closer look, never enter orbit, never send back detailed images from within the system. It would be a blur passing through, a silent visitor that sees everything once and never returns. This reality changes how we think about interstellar exploration. Speed is not enough. The ability to stop, or at least slow down, is what turns a flyby into an encounter. Without deceleration, all we can ever do is glance at the stars as we rush past them. But slowing down after accelerating to such enormous speeds requires as much or more energy than the journey itself. In spaceflight, every maneuver costs energy, and that energy must come from somewhere. On Earth, we can rely on friction, drag, and atmosphere to help slow things down. Space offers none of that mercy. To slow down by propulsion alone, a probe must carry enough fuel to cancel its own momentum. The faster it went, the more fuel it would need to stop. But every bit of fuel adds mass, and the heavier the probe, the more fuel it needs to move at all. This creates a vicious loop, the rocket equation in its purest, most unforgiving form. A probe designed to reach even a tenth of light speed would require thousands of times its own mass in fuel just to accelerate, and the same again to decelerate. That's why most interstellar mission designs quietly skip the deceleration part. The breakthrough Starshot concept probes, for example, have no braking system. When they reach Proxima Centauri, they will flash through the system in seconds. Their onboard cameras would have to record everything in an instant, transmitting what little they can before the signal fades. The journey would take more than 20 years, but the encounter would last less than the blink of an eye. The dream of entering orbit, studying Proxima B's surface, or landing instruments on its soil, all of that remains impossible with current thinking. Some have proposed clever solutions. One idea is to use the destination star's own light as a brake. Just as a sail can catch photons to accelerate, it could also be used in reverse, turning the sail to face the oncoming light, letting radiation pressure slow the ship. In theory, this could work, but only if the sail is enormous, reflective, and nearly indestructible. And even then, the force of starlight is tiny. It would take years to bleed off speed, and the probe would have to pass very close to the star to get enough light pressure. The heat and radiation would likely destroy the sail long before the ship stopped. Another proposal is to use magnetic fields as a kind of cosmic parachute. Space is filled with sparse particles and magnetic fields from the interstellar medium. A probe could deploy a magnetic field ahead of it, sweeping up charged particles and using their resistance to slow down. This is called a magnetic sail, or magsail. The idea is elegant, using the thin plasma of space as a natural brake, but the physics are brutal. The density of interstellar matter is so low that even a powerful magnetic field would take decades to slow a ship traveling at high speed. The magsail would have to be huge, spanning kilometers, and the structure would need to survive collisions with high-energy particles at relativistic speeds. Like so many ideas in interstellar engineering, it works beautifully on paper, but collapses under real-world conditions. Some scientists suggest using the gravity of the destination star as a brake, swooping close to it to trade speed for trajectory. But that gravity assist only changes direction. It doesn't reduce overall velocity unless the ship can also push against something else, like a planetary atmosphere. And in another star system, there are no guarantees of planets or atmospheres suitable for that purpose. Even if they exist, the precision required to hit such a target at a fraction of light speed is almost unimaginable. A small navigation error made years earlier would send the probe past the system entirely. In every scenario, the same truth emerges. Slowing down is harder than speeding up. Acceleration can be achieved in many ways, but deceleration always demands interaction with something external. And in interstellar space, there's almost nothing to interact with. Every kilogram of propellant that could be used to slow down must be carried from the start. It's a trap built into the fabric of physics. The deceleration problem also shapes what kind of missions are even possible. A human expedition, for example, would be impossible without a way to stop safely. Even at modest fractions of light speed, the energy required to decelerate a crewed ship would equal that of several nuclear arsenals. There's no known material that could withstand the heat or stress of braking under those conditions. And if the ship simply coasted past its destination, there would be no second chance. The crew would continue drifting through space forever, unable to turn back. One far future idea to solve this problem comes from the notion of using twin laser systems, one on Earth to accelerate, another in the destination system to decelerate. The ship would approach, turn its sail around, and let the incoming light push against it to slow down. It's symmetrical and elegant, but it assumes something crucial, that a laser system already exists at the target. In other words, we could only slow down if someone, or something, was already there to help us. For now, that remains science fiction, though it hints at the scale of cooperation that true interstellar travel would require. The more realistic conclusion is that the first journeys to the stars will not stop. They will be glimpses, not visits. Probes will rush through alien systems, recording as much as possible before disappearing into the void. It's the same way Voyager once passed Jupiter and Saturn, moments of breathtaking discovery achieved in brief flybys. The act of reaching another star, even without stopping, would still be a triumph. It would mean that something built by human hands crossed the gulf of interstellar space. Yet the deceleration problem reminds us that the universe doesn't make such achievements easy. Momentum is both our greatest ally and our greatest enemy. It carries us forward, but it also traps us in motion. Once you are moving fast enough to cross between stars, stopping becomes the hardest thing in the cosmos. Once you begin a journey of that scale, you can never truly turn back. The ship becomes part of the endless flow, another drifting particle among the stars. A silent arrival in a dead system. Imagine for a moment that every challenge has been overcome. The aim was perfect, the course held steady for decades, and the probe arrived exactly where it was meant to. After a century of travel, it slows just enough to turn its cameras and instruments toward the planet we've dreamed of for years. Somewhere on Earth, scientists are waiting for the first signal, knowing it will take more than 4 years just to cross the void between stars. They know that when it comes, they'll be receiving light from a machine older than anyone alive, carrying images from a world no human will ever touch. It would be one of the greatest scientific moments in history. But what if what it found was nothing? No oceans, no air, no motion, only rock. The cameras might reveal a cracked and lifeless surface, scorched on one side by constant daylight, and frozen solid on the other. The data might show no trace of an atmosphere, no magnetic field, no signs of life at all. The planet might be sterile, its surface battered by radiation and dust, a silent tomb circling a faint, violent sun. After all the years of waiting and all the centuries of planning, the dream of a new Earth could end in a single line of code, no signs detected. In that moment, success begins to look strangely like failure. The probe did everything it was designed to do. It traveled across interstellar space, survived impacts, held its course, and gathered data. Yet the outcome offers no warmth, no revelation of a living world waiting for us. The achievement would still be monumental, but emotionally, it would feel hollow. It would mean that even the nearest star system, the most reachable one in all the galaxy, holds no echo of us. The silence that follows the transmission would feel louder than any discovery. It's not hard to imagine what that data might show. Proxima B may be a world stripped bare by the very star that gives it light. The planet's rocks might glow faintly under the constant bombardment from Proxima Centauri, but they would never host life as we know it. A probe arriving in such a place would find a sky that never changes. One hemisphere would be locked in endless day, the other in endless night. On the day side, the surface might shimmer with heat and dust, its horizon blurred by static storms. On the night side, a thin crust of frost might stretch for miles, water vapor frozen into eternal darkness. In between, in the narrow twilight band where day meets night, there might be faint traces of old erosion, hints that liquid once flowed there. But time would have erased it all. No wind, no waves, no sound. Just a planet slowly circling its star in total quiet. If that were the outcome, how would it feel back on Earth? The signal would arrive as a stream of numbers, a heartbeat of radio waves from a machine so distant it could barely be believed. Scientists would translate those numbers into images, the first close look at another planet around another star. For generations, humans had imagined this moment as a meeting, a kind of reunion with the wider universe. But the first image might look more like a graveyard, a cracked desert under a dull red sky. The data would confirm what reason always suspected, that proximity does not mean promise. There would still be awe. The mere fact that something built by human hands reached another star would be enough to redefine history. But alongside that, awe would come something quieter, something heavier. The realization of just how alone we might be. After a century of travel and the work of countless generations, the first contact with another world could be with one that doesn't answer back. The silence from Proxima B would be existential. It would tell us that even the nearest world might not share in the miracle of life. The people studying those transmissions might not express it openly, but there would be a deep sense of loss in their voices. Not the loss of the probe or of the mission, but of an idea, the hope that something waited for us out there. The raw data would be analyzed, archived, and celebrated, but after the excitement faded, what would remain would be an empty kind of victory. We would have proven that interstellar exploration is possible, only to discover that the reward was dust. That silence would be a truth we had to face, that space does not owe us beauty or life or comfort. The universe is not arranged for our satisfaction, it simply is. The probe's success in reaching Proxima B would not change that, but it would give us a clearer picture of reality. For centuries, we've looked at the stars and imagined companionship. Maybe this discovery would teach us to see the cosmos not as a mirror of our hopes, but as something vast, indifferent and magnificent in its own right. It's strange how easily we project life onto what we don't understand. The phrase Earth-like planet invites us to imagine green fields, oceans and blue skies. But Earth-like really just means rocky and roughly the right temperature. The details, atmosphere, chemistry, magnetic protection, decide everything. Proxima B might check some of the same boxes as Earth, but it may never have shared our story. The conditions that make life possible here are balanced on a knife's edge. Shift that balance by even a little, and you get a world where nothing moves. If the probe sent back images of that lifeless terrain, humanity would have to decide how to interpret them. Some would see disappointment, others perspective. It would remind us that our own world, for all its flaws, is astonishingly rare. The contrast between the living Earth and the dead Proxima B would show how fragile life really is. It might shift our focus inward, toward preservation rather than expansion, a kind of cosmic mirror reflecting what we already have. But there's another way to look at it. Even if the planet is lifeless, the act of finding out still matters. The silence itself would be a discovery, proof that we can look across the light years and know something true about another sun. We would have reached the point where imagination gives way to evidence. That alone would mark a turning point in human history. We would no longer just dream about other worlds. We would have touched one in a way and found it empty. And in that emptiness, there's a strange kind of purity. It is reality stripped bare of all illusions, forcing us to accept the universe as it is. The engineers who built the probe might never live to see its arrival. Their children or their grandchildren might be the ones to receive its final data. By then, Earth itself could be unrecognizable. New nations, new technologies, maybe even new problems that make the mission seem distant. And yet, somewhere in the background noise of deep space communication, the signal would arrive, a whisper from another star saying, "I made it, there's nothing here." It would be both the saddest and most beautiful message humanity has ever received. This outcome, a lifeless world, a silent system, is also the most likely one. Most planets we've found so far are barren, scorched or frozen. The universe appears to be built more for emptiness than abundance. Proxima B might fit perfectly into that pattern. Its quiet might not be a tragedy, but a reflection of nature's vast indifference. Still, the contrast between our hopes and that reality would sting. It would force us to face the limits of our longing, to admit that sometimes success changes nothing. The cost of cosmic patience. We often picture the moment of launch, or the dramatic first signal from a distant world. But in between those two moments lies a gulf of time so large that it tests not just engineering, but the endurance of human attention itself. The idea of a mission to Proxima B sounds thrilling when we think in years or even decades. But when the timelines stretch into centuries, everything we understand about science, culture, and commitment begins to unravel. Realistic designs might take hundreds or even thousands of years. During that time, entire languages could vanish, cities could crumble, nations could fall, and the memory of why the probe was launched could fade into myth. Our society operates on short feedback loops. Political terms are counted in years, scientific grants in shorter periods still. We struggle to think in centuries, let alone millennia. To commit to a project that will not yield results within a human lifetime requires a shift in mindset, away from curiosity seeking immediate reward, toward patience that expects none. It asks for a belief in continuity across generations, that people yet unborn will care about something that was started long before them. History gives us a few glimpses of this kind of endurance. The cathedrals of Europe were built over hundreds of years, with the first stone laid by workers who knew they would never see the roof completed. Ancient observatories were carved by civilizations that no longer exist, yet their purpose, to study the heavens, still resonates with us today. The Voyager probes, launched in the 1970s, are perhaps the closest modern parallel. They are still flying, still whispering faint signals back to Earth, though the team that built them has mostly retired or passed away. Voyager's messages take nearly a full day to reach us now, and soon the probes will go silent. But the mission continues to remind us that exploration is not always about arrival. Sometimes it's about persistence. A probe to Proxima B would magnify this challenge beyond anything we've attempted. It would be a mission built by one civilization, guided by another and received by a third, all separated by time. The original team would be gone before the probe reached even a fraction of its journey. The scientists interpreting its data centuries later might live in a world unrecognizable to us. They might have different priorities, different tools, or even a different understanding of what life means. The knowledge we send might seem primitive to them, or the results meaningless. The problem is that human society does not operate like a relay race. There's no guarantee that the next generation will pick up the baton. Wars, economic collapse, or shifts in ideology can erase scientific programs almost overnight. Records can be lost, and digital archives can decay. Even if the probe survived the journey, the receivers on Earth might not exist anymore. Or if they did, they might not remember what they were waiting for. This idea that we could send something out and never be there to receive its message creates a strange emotional tension. It's both humbling and haunting. The cost of cosmic patience isn't just measured in time, but in detachment. It forces us to give up the idea of reward. To build something that will work for hundreds of years means designing machines that can think and repair themselves, because no one will be there to help. It means trusting that future minds, perhaps evolved beyond our own, will one day decode the signals we sent with our crude early instruments and understand the story behind them. And yet, we have done similar things before. We bury time capsules, we write books, we build monuments that we hope will outlast us. Each of these acts comes from the same instinct, to reach forward into a time we cannot touch. An interstellar probe is simply the most ambitious expression of that instinct. It's a time capsule flung into the dark, not for us, but for whoever comes after. The patience it demands is cosmic, not just in duration, but in spirit. It asks us to see ourselves as part of something larger and slower, a species learning to leave a trace beyond its own lifespan. But patience costs resources too. The longer a mission lasts, the harder it is to maintain funding, interest, and infrastructure. Even the most noble scientific projects compete with the needs of the present: hunger, energy, conflict. Convincing governments to invest in something whose outcome no living person will witness requires almost mythic storytelling. It needs faith in the idea that progress can outlast politics. If a probe stops working after 50 years, is that failure? What if it survives for 500 but never sends a signal? What if, by the time it arrives, humanity has moved beyond physical exploration altogether, communicating across the stars by other means? The measure of success would depend not on arrival, but on endurance, whether the mission itself inspired continuity of thought. The farther we try to reach, the more we confront our own fragility. Our bodies decay within a century, our institutions within decades, and yet we want to touch something that will take millennia to reach. It's a beautiful contradiction, a species bounded by time, reaching for eternity. This is the true cost of cosmic patience, realizing that we will never know the ending of our own stories, yet choosing to write them anyway. The first humans who looked up at the night sky did not know what stars were. They saw lights that never moved and called them eternal. Today we know they are suns, distant, burning, and temporary. But still, we reach toward them. Even if our machines fall silent before they arrive, the act of trying means that, for a brief moment in cosmic time, a species born on one small planet dared to imagine a connection across the void, and had the patience to try. Building a mission that outlives civilizations. Every piece of technology we make has an expiration date. Metal corrodes, circuits degrade, batteries drain. Even the most carefully shielded systems will eventually suffer the slow breakdown of atomic bonds, the creeping influence of radiation, and the silence of entropy. A probe sent to Proxima B would face all of this for hundreds or even thousands of years. It would have to survive without maintenance, without upgrades, and without help. Its hardware would need to be not just durable, but timeless. The first challenge is power. Every spacecraft ever built depends on energy to live, to heat itself, to run instruments, to send data. For deep space probes, That energy comes from either solar panels or radioisotope generators. But sunlight fades to almost nothing once a spacecraft leaves the outer planets, and radioisotope power sources have limits too. The plutonium that fuels them decays over time, its output falling steadily each decade. After a few centuries, it's gone. For a mission that must outlast civilizations, we have no proven way to keep the lights on. Some have proposed small nuclear reactors that could restart themselves after dormancy. Others suggest advanced batteries charged by cosmic rays, or even magnetic induction from interstellar fields. But all of this remains a theory. Then there's the question of materials. Most metals expand and contract with temperature swings, cracking over time. Plastic becomes brittle, glue weakens. Even silicon chips are vulnerable to radiation damage, their transistors slowly corrupted by the energetic particles that constantly move through interstellar space. Shielding can help, but only so much. The thicker the armor, the heavier the spacecraft, and weight is the enemy of distance. Engineers face an impossible trade-off. Build something strong enough to last, and it may never get off the ground. Build it light enough to travel, and it may not survive the trip. Software adds another layer of fragility. Even if the hardware endures, the code must too, and code is far more delicate. It can't simply be frozen and forgotten. It must adapt to changing conditions, correct its own errors, and recover from unforeseen events. That means artificial intelligence, but not the kind we use on Earth. It must be something that can learn without human oversight, yet never drift too far from its mission. It must be careful, cautious, endlessly patient, a mind that never sleeps, existing in the quiet between the stars. Building such intelligence is as much a social problem as a technical one. We would have to decide what kind of personality a mission should have. Should it follow its instructions blindly or improvise when it encounters something unexpected? Should it protect itself at all costs or risk damage to gather data? These are ethical questions, asking us to define what exploration means when no human will ever be there to guide it. And then, even if all of that succeeds, the power, the materials, the code, there's the problem of language. Every message the probe sends, every bit of data it stores, will eventually need to be read by someone. But languages evolve. English today is already drifting away from the English of the early 1900s. 1,000 years from now, it might be as unreadable as ancient Greek or Sumerian. Even binary data, if the context is lost, could become meaningless noise. Future scientists might receive the signal but not understand what it represents. This has already happened on Earth. The earliest computers stored data on media that can no longer be read by modern machines. Whole libraries of early digital records are now useless because no one preserved the devices needed to interpret them. A civilization that sends a probe across light years must therefore design not just a machine, but a message that can survive the erosion of understanding. It must assume that its own descendants might not speak its language, share its symbols, or even think in the same ways. Some scientists have suggested encoding universal patterns, mathematical constants, atomic structures, or simple logic diagrams, things that any intelligent being could, in theory, recognize. The Voyager Golden Record took this approach. It carried sounds, images, and instructions etched into a metal disc, along with a diagram showing how to play it using fundamental constants of hydrogen. But even that may not be enough. Mathematics feels universal to us, but it is still shaped by how we perceive the universe. A species, or a future humanity, that has moved beyond our sensory limits might not see meaning in the same way. Beyond the problem of understanding lies the challenge of stewardship. A mission that outlives civilizations cannot depend on any single organization, country, or culture. NASA might start the journey, but who ensures it continues when NASA no longer exists? Private foundations can fail. Governments can collapse. Even global institutions are temporary on cosmic timescales. For a mission to truly outlast civilization, it must become something self-sustaining, not a project owned by one era, but a legacy that all future generations agree to maintain. This could mean distributing its care across multiple groups or even embedding its purpose into cultural myths. A story passed down, ensuring that no matter how the world changes, people will still remember why a small machine was sent into the dark. It's a strange thought. To keep a mission alive, it might need to become more than a scientific project. It might need to become part of our shared identity, a kind of spacefaring heritage. Some have compared this to the great libraries of the past, the Library of Alexandria, for example. It was built to preserve knowledge for all time, yet it burned. Later civilizations built new ones, and they too were lost. Knowledge, it seems, is more fragile than stone. The same could happen with an interstellar mission. The technology could survive, floating through the void, but the knowledge of how to listen might not. The signal could reach Earth centuries later, only to find silence. Designing against that possibility forces us to think differently. Maybe the solution is redundancy. Many copies of the probe, each with slightly different systems, each carrying the same message in different forms. Maybe the data should be transmitted back not once, but continuously, repeating itself like a beacon through time. Or maybe the mission should carry its own instructions for reawakening, a cosmic manual encoded so deeply into its systems that any intelligence, human or otherwise, could rediscover its purpose. Whatever the approach, we would have to admit that we cannot predict the future, that what we build will outlive our culture, our language, and maybe even our species. We would be designing not for our successors, but for the unknown. That means simplifying, not complicating. It means choosing durability over elegance, clarity over cleverness. The goal would not be to build the most advanced probe, but the most understandable one. The limits of human promises. Consider the great projects of the modern world, scientific experiments that took generations of work, like particle accelerators or deep observatories. The Large Hadron Collider was once the greatest human instrument ever built. Yet only a few decades after its first experiments, funding debates and political fatigue threaten its continuation. The same story unfolds across fields. Telescopes lose funding before they even complete their missions. Space agencies change course with every election, and decades of planning can vanish with a single policy shift. It's not because humanity doesn't care about knowledge. It's because we live in cycles. Our priorities evolve with generations. Each one inherits the unfinished dreams of the last, but also its debts and its distractions. The future, to us, is always something we will attend to later. We build as if permanence were guaranteed, yet act as if only the next quarter or the next administration matters. Even our monuments to endurance, things designed to last, rarely escape decay. The Arecibo radio telescope once symbolized humanity's long ear to the cosmos. For decades, it listened to whispers from the stars, part of the same dream that imagines reaching Proxima Centauri. Then, quietly, it fell apart. Cables snapped, panels collapsed, and soon the structure was gone. There was sadness, but also acceptance. No one rebuilt it. The world had moved on. A similar fate has met many observatories, laboratories, and exploration programs that were once icons of discovery. Our attention is not infinite. Projects that last centuries depend on generations who didn't start them, but are asked to care as deeply as those who did. That's a difficult inheritance to keep alive. Even cultural traditions, stories, languages, and art change over far shorter spans. We can barely preserve meaning within our own families over a few generations, let alone across millennia. Nations dissolve, universities close, corporations shift goals. Funding structures depend on economies that rise and fall. A project that depends on any of these for survival will eventually falter. That's why so many scientific endeavors are short-term. They must fit into political calendars, grant cycles, and media attention spans. The deep timescales of the universe simply don't match the short rhythms of human society. There have been attempts to challenge that. The Long Now Foundation, for instance, is building a clock designed to keep time for 10,000 years. It's a symbolic act, a reminder that thinking beyond the next century is possible. But even that project depends on human curiosity and care to survive. The clock might keep ticking in silence, but unless someone remembers why it matters, it becomes just another artifact, another mystery in the dust. The same logic applies to interstellar ambitions. History doesn't give encouraging answers. Great works are forgotten because meaning itself fades. The builders of Stonehenge, for example, left no written records. Today we can measure the stones, model their alignments and speculate about their purpose. But the intention, the true meaning behind the act, is lost. The same could happen to our greatest technological creations. One day, archaeologists might dig up the remains of our deep space transmitters and wonder what they were for. Long-term promises depend on faith, but faith is fragile when stretched across centuries. Even within a lifetime, human commitments waver, treaties are broken, environmental pledges fade. We promise to care for the planet and then forget the promise when it becomes inconvenient. Why would our future selves treat a distant spacecraft any differently? Some might argue that automation solves this, that we don't need humans to remember if machines can do it for us. But even automation requires maintenance. Even the most perfect design can't protect against entropy forever. More importantly, automation doesn't preserve meaning. Machines can keep working, but they can't tell us why they should. Without the thread of purpose, they become silent relics of forgotten intentions. Our species dreams further than any other known life form, yet we struggle to stay focused long enough to realize those dreams. We speak of colonizing planets, yet can barely manage infrastructure that lasts a century. We plan for stars, yet replace our devices every few years. In many ways, our civilization is built on the temporary. Disposable goods, short careers, fast news, fleeting trends. The long view feels unnatural, almost alien. That's not to say we are incapable of long-term thinking, only that it comes at a cost. It requires discipline, stories, and shared meaning that stretch beyond individuals. The medieval cathedrals were maintained because religion remained central to culture. If that had changed faster, they might have been abandoned halfway through. In our age, science itself is under constant redefinition. What one era calls essential, another might call outdated. Future generations might see interstellar travel not as noble, but as wasteful. Can a civilization like ours, dynamic and restless, truly build something meant to last? Or are we, by nature, too fluid to hold to any one goal that long? The paradox of progress is that the same creativity that drives us forward also pulls us away from continuity. We innovate by breaking from the past, not by preserving it. Every generation seeks its own frontiers. It's an uncomfortable truth. Our attention span may be the final barrier to the stars. Every rocket we've built, every telescope we've raised reflects a moment of focus, a spark in time. But stars demand more than sparks. They demand steady flame, burning through centuries of change. Can we sustain such a flame? The telescope that replaces the ship. Telescopes have always been humanity's most powerful spacecraft because they let us see without moving at all. The further our instruments reach, the more they begin to replace the need for travel. Where rockets face the hard limits of fuel, speed, and survival, telescopes expand only through ingenuity. And in that sense, they may be the only vessels that can truly reach other worlds within a single lifetime. This shift has already begun. The JWST, launched in 2021, was designed to look not just at stars and galaxies, but at planets orbiting them. By analyzing the faint light that passes through a planet's atmosphere when it crosses its star, Webb can detect molecules, water vapor, carbon dioxide, methane. It can't yet show us oceans or continents, but it can show the fingerprints of chemistry. For the first time, we are starting to read the skies of other worlds from across interstellar space. It feels almost like cheating. Instead of spending generations building a ship to cross the void, we stay home and let light do the traveling for us. Photons, tiny packets of energy, are the fastest messengers in the universe, and they've been crossing the gap from Proxima Centauri to Earth long before we existed. A telescope like Webb doesn't need to go there. It only needs to catch the light that already has. Every flicker, every wavelength, every faint dip in brightness becomes a clue. This is what makes modern astronomy so different from the early days of exploration. When Galileo looked at the moon through his crude telescope, he saw mountains and shadows. When the Hubble Space Telescope opened its eye in the 1990s, it revealed galaxies so distant that their light began its journey before the Sun was born. Now, with JWST, we are studying the thin atmospheres of planets dozens of light years away, searching for chemical signs that could mean life. The line between telescope and spaceship is beginning to blur. We are learning to travel by seeing. On one hand, telescopes can do things no probe could ever achieve. They can survey thousands of stars at once, analyze their planets, and build a statistical picture of how common habitable worlds might be. On the other hand, the data they provide is always indirect. It's like studying a distant forest only through the color of the light reflected from its canopy. Enough to know it exists, but never enough to touch the bark or smell the air. That limitation drives the next step, even more powerful telescopes. If Webb is the beginning, missions like LUVOIR, HABEX, and the Origin Space Telescope are the next leap. LUVOIR, the large UV/optical/infrared surveyor, is a concept for a giant space telescope, many times larger than Hubble or Webb, with a mirror so wide it could fold out like a blooming flower once in orbit. With it, scientists hope to not just detect exoplanets but image them directly, to see pale blue dots that truly resemble Earth. Direct imaging is one of the hardest goals in astronomy. The glare of a star is so overwhelming that it can easily drown out the faint reflection of any planet beside it. It's like trying to see a firefly next to a lighthouse from thousands of kilometers away. To overcome that, engineers are developing techniques to block out the star's light with extreme precision. One of the most elegant ideas is the star shade, a vast flower-shaped screen that could fly tens of thousands of kilometers away from a telescope, perfectly aligned so it casts a tiny artificial eclipse. Behind that shadow, the planet's own faint light would finally be visible. Imagine what that means for a place like Proxima B. If we could block out Proxima Centauri's brightness and isolate the planet's reflection, we might see hints of clouds, continents, or ice caps. We could study its weather, measure its seasons, and determine whether it truly has an atmosphere or liquid water. In other words, we could do most of what a visiting probe would, without ever leaving home. And unlike spacecraft, telescopes improve exponentially over time. Every generation brings larger mirrors, sharper sensors, and new wavelengths. Earth's surface is now dotted with giant observatories that can rival space telescopes using adaptive optics, systems that adjust their mirrors in real time to cancel the blurring effect of Earth's atmosphere. Telescopes like the extremely large telescope in Chile and the 30-meter telescope in Hawaii will have mirrors the size of small buildings, capable of resolving details once thought impossible from the ground. As these instruments come online, our picture of exoplanets will sharpen. We'll be able to detect subtle chemical imbalances that might indicate biological activity, oxygen that isn't balanced by other gases, or methane that suggests active replenishment. We might even detect seasonal changes, suggesting a living world that breathes. These discoveries won't require a ship, only patience and precision. Humanity spent centuries dreaming of visiting the stars, but perhaps that dream was always foolish. Each photon that strikes a telescope's mirror carries a fragment of another world's story. By catching enough of them, we can piece together that story without ever leaving the comfort of our orbit. The telescope becomes a bridge. This approach changes how we think about interstellar exploration. The old model was physical. The new model is informational. We gather light, decode its patterns, and reconstruct distant realities from here. It's a quieter kind of adventure, one that depends on mathematics and patience rather than engines and fuel. But it may be the only kind that works on cosmic scales. A telescope doesn't just observe, it travels through time. The light it captures from a distant planet began its journey years, sometimes centuries ago. When we look at Proxima B, we are already seeing its past. a frozen image of what it was years before. Every observation is a kind of time capsule. The more we improve our instruments, the more we can reconstruct the layers of that capsule, its history, its chemistry, its place in the cosmic web. The same limitations that stop us from traveling, distance, energy, time, have forced us to become cleverer at watching. We can't touch these worlds, so we learn to read them from afar with incredible accuracy. In doing so, we may come to understand them more deeply than we would if we could actually go there. The ship's dream is romantic, but the telescope's gaze is eternal. Even if we never stand on another planet, these telescopes will change how we see ourselves. By comparing Earth's atmosphere to those of other worlds, we'll learn what makes ours rare. We'll see how fragile its balance of gases really is, how temporary its life-supporting conditions might be. From a distance, Earth will look like just another pale dot, and that realization alone could reshape how we think about survival, responsibility, and the meaning of home. Seeing more than we can touch. In space exploration, it's easy to believe that the ultimate goal is to go somewhere, to land, to touch, to leave footprints. But as our instruments become more powerful, that idea starts to change. A telescope doesn't just take pictures. It breaks light into parts, into a spectrum, and reads the faint signatures imprinted within it. Spectroscopy works like a cosmic barcode scanner. Each chemical element absorbs and emits light at specific wavelengths. When light from a distant planet's atmosphere passes through a telescope's instruments, certain parts of that light are missing, absorbed by gases along the way. By studying which wavelengths disappear, scientists can identify what those gases are. If there's water vapor, it leaves one kind of pattern. If there's methane, another. If there's oxygen and ozone, that's something else entirely. Something that might mean life. Instead of soil samples or photographs, astronomers collect data. Long lists of numbers, brightness levels, spectral lines. They run these through models to reconstruct what an atmosphere must look like, what kind of clouds it might have, how thick it is, how hot it gets during the day. From these abstractions, an image of the world emerges, and that image can sometimes tell us more about a planet's reality than any camera could. A probe landing on another world can only explore a tiny patch of ground. But spectroscopy lets us study an entire atmosphere at once. It can detect gases mixed miles above a planet's surface, reveal storms, and track seasonal changes over years. The data builds a living picture, one that changes over time, showing whether a planet is stable, chaotic, or teetering between the two. This kind of remote sensing has already transformed our understanding of the universe. When astronomers first applied it to Jupiter and Saturn, they discovered layers of clouds and complex chemistry no probe had ever seen. When it was used on Venus, it revealed a choking atmosphere of carbon dioxide and sulfuric acid, a warning of how different a planet can become under runaway heat. Now, the same technique is being pushed to its limits to analyze worlds around other stars. Even the smallest signals can carry enormous meaning. In 2023, data from JWST revealed hints of carbon dioxide and methane in the atmosphere of a planet called K218b. But what truly caught attention was the possible detection of a rare molecule called dimethyl sulfide, a compound that, on Earth, is mostly produced by life. It's far from confirmation, but it shows how detailed light analysis has become. From over 100 light-years away, we are already beginning to detect the chemical whispers of biology. The next generation of telescopes will make these whispers clearer. Missions like HABEX will not just measure atmospheres, they'll map them. They'll be able to tell where clouds gather, how temperatures shift between day and night, and whether sunlight reflects off oceans or deserts. Imagine detecting the glint of light off an alien sea, a shimmer so faint it's almost invisible, yet enough to confirm the existence of liquid water on another world. As our algorithms and instruments improve, the amount of detail we can extract will only grow. Artificial intelligence is already helping astronomers find hidden patterns in massive datasets, variations too subtle for humans to notice. These patterns might reveal volcanic activity, vegetation like color shifts, or chemical cycles that come and go like seasons. We already use similar methods to study Earth from space. Satellites constantly monitor our planet's atmosphere, oceans, and vegetation using spectroscopy. They detect changes in air composition, track wildfires, and measure plant growth. Now we're applying the same principles outward, scaling them across light years. In a way, the Earth has become the training ground for reading other worlds. No human could survive the radiation around a gas giant or the thin air of a distant planet, but our instruments can. They can see in wavelengths our eyes will never perceive: ultraviolet, infrared, radio. They can listen to the electromagnetic hum of worlds that have never seen sunlight. Through them, our perception is evolving into something almost omnipresent, capable of seeing the unseen and touching the untouchable. There's a kind of paradox in this progress. The more clearly we see other worlds, the less we might ever need to visit them. If a telescope can map a planet's surface, detect its biosphere, and predict its climate, then a physical landing may be little more than symbolism. The universe could become a place we know intimately but never physically enter, like reading a detailed biography of someone we'll never meet. One day, these techniques may reach the point where our telescopes can identify surface vegetation, even detect color changes that suggest the growth and decay of ecosystems. We might learn to read an alien planet the way we read Earth from space, by its reflection, its temperature, its subtle rhythms. We'll have learned to see without touching, to know without going. In that sense, the telescope and its data are evolutions of rocket ships. They carry us further, and the more we refine our ability, the more we realize that perhaps we've already been exploring the universe all along, not with our feet, but with our minds. From exploration to simulation. As computing power grows, the line between observation and creation begins to blur. What if, instead of building a ship to visit another world, we could build that world in code, atom by atom, photon by photon, until it was real enough to explore? Humanity's tools are slowly reaching that point. Artificial intelligence, physics engines, and data-driven models can already reconstruct distant planets using fragments of light. With each improvement, the gap between physical travel and digital experience narrows. A simulation doesn't sound as thrilling as a mission to another star, not yet. But that's because today's virtual worlds are crude compared to what could come. In the far future, entire planetary environments could be recreated using real astronomical data. The terrain, the weather, even the chemical composition of the air could be modeled precisely. It might not be a guess at all. It could be the closest thing to standing there without ever leaving home. The universe we see through our instruments is already a reconstruction. The colors, the brightness, even the distances we perceive are all products of interpretation. Light turned into information, then into images our minds can grasp. So, in a way, we've been simulating reality for a long time. We've never seen a star or planet directly with our eyes. We've seen the filtered, processed version that instruments allow us to see. Extending that process to complete virtual models is not such a leap. The difference is that one day, those models could be interactive. We could walk through them, touch them, and study them as if they were real. For most of human history, exploration required risk, cold, hunger, danger, the unknown. It was an act of bravery because it meant stepping into a place where help could not reach you. But if exploration becomes something we can do from the safety of a simulation, then it transforms from a physical challenge into an intellectual one. The frontier moves inward, into the realm of computation, creativity, and thought. We would still explore, but the explorers of the future might use algorithms instead of rockets. It's easy to imagine how such simulations could be built. The data gathered by space telescopes could provide the foundation, precise measurements of a planet's size, orbit, and atmospheric makeup. From there, physical models could fill in the missing details, cloud patterns driven by known equations of fluid dynamics, surface colors determined by mineral compositions inferred from spectra. As the model runs, it refines itself, learning from each new observation. What results is an evolving mirror of a real world, driven by the same physics that shapes it light years away. In this kind of future, every major discovery would immediately become accessible to everyone. You wouldn't need to read about Proxima B in a scientific paper. You could step into it. The data that describes the planet could be translated into a fully navigable landscape, where scientists could test hypotheses by direct interaction. How would the light from its red sun scatter through a thick atmosphere? What would the temperature feel like at dawn? These are questions no telescope could ever answer, but a well-built simulation could. And perhaps most surprisingly, such a world might feel emotionally real, beautiful, alien, even haunting. If we can simulate a world perfectly enough that it behaves as the real one would, then what difference does it make whether we visit it physically? Our senses would register the same experiences. Our understanding of its nature would be the same. The meaning of exploration might no longer depend on distance or physical presence, but on understanding and experience. Perhaps the future explorers will not be astronauts, but architects, people who build realities that let us feel what the universe is like, without having to reach it. Yet this idea raises uncomfortable questions. If simulation becomes our main way of exploring, will we lose something essential? The thrill of risk, the pride of achievement, the feeling of touching something that truly exists. All of that could fade. The physical journey, with its hardships and uncertainty, has always given exploration its depth. Without it, would discovery still carry the same weight? Would the simulated mountains of an alien planet inspire the same awe as the first footprints on the moon? Some might argue that it wouldn't matter. For most people, exploration has always been a story experienced secondhand, through images, books, or broadcasts. Only one man watched Neil Armstrong's step in person, but millions felt something profound while seeing it on a screen. A perfect simulation might simply bring that experience closer, more vivid, more personal. It could democratize wonder. Everyone could have their own mission, their own encounter with the unknown, tailored to their curiosity. In that way, the dream of exploration could expand rather than shrink. But others would see it as a quiet retreat. The shift from Starship to simulation could be read as humanity giving up, accepting that the stars are too far, the challenges too great. We might tell ourselves that simulations are good enough, that reality is overrated, while deep down knowing it's a compromise. Over generations, that could change how we think about ambition. Why build ships if we can build worlds inside computers? Why take centuries to travel when we can invent the view instantly? The convenience could dull the very drive that once made us reach for the impossible. And yet, in another sense, simulation might be a natural continuation of exploration, the same impulse, translated into a new form. What drives exploration is not physical movement, but curiosity. It's the desire to see what has never been seen, to understand what was once unknown. If technology allows us to do that more effectively, perhaps it doesn't matter whether we move through space or through information. A perfect model of a world 4.24 light-years away could reveal truths no ship could ever capture. It's also possible that this new form of exploration could lead us back to the real stars. Simulations could become training grounds, places to test ideas, build intuition, and prepare for missions that will one day be real again. The virtual could make the physical more achievable. By living inside models of alien worlds, scientists might better understand how to design probes and habitats for the real thing. The imagination, powered by data, could be the first step toward genuine travel once more. In that sense, the simulation is a bridge that keeps curiosity alive during the long pauses of history. The centuries when no ship flies, when funding ends, when dreams wait for technology to catch up. Virtual exploration might be what keeps the flame burning until the engines are ready again. It could remind us of what lies out there, even when we can't yet reach it. And when that day finally comes, when a probe or a crewed ship does head toward another star, it may carry with it maps and models built from centuries of simulation. The astronauts or machines who arrive will already know the terrain, the weather, the colors of the sky. They will have walked that world many times before, virtually, in preparation for the moment when fiction turns to reality. In that way, the two forms of exploration are not enemies, but partners. One keeps the dream alive, the other fulfills it, the digital colonization of the stars. There's a different way to imagine humanity reaching the stars, not by moving our fragile bodies through space, but by sending something lighter, faster, and far more durable. In this vision, the explorers are not made of flesh and bone, but of information. Instead of a ship carrying humans, there's a stream of data, an encoded mind, a digital consciousness, a self-contained intelligence built to survive the cold vacuum of interstellar space. This idea replaces movement with transmission. It replaces colonization with replication. It turns exploration into something that can happen at the speed of light. Scientists and futurists have talked about this for decades, the possibility of transferring a human mind into a digital form, not as a copy, but as a continuation, a mind running on silicon rather than neurons. If that ever became real, the implications for space exploration would be enormous. A digital mind wouldn't need air or food. It wouldn't care about radiation or zero gravity. It wouldn't age and it wouldn't die, at least not in the way we do. You could send millions of them, compressed into tiny data packages, across the void between stars. They could travel as laser signals, carried by light, and rebuild themselves on the other side, if something is there to receive them. This is what some thinkers call digital colonization, the spreading of consciousness rather than bodies. It's not about landing on a planet and building cities. It's about transmitting awareness, thought, and memory. A civilization could fill the galaxy, not with buildings and machines, but with software. Worlds could be colonized not by people, but by their digital descendants. Minds that think and remember, even if they no longer breathe. It's a strange and unsettling idea. The stars might one day belong to our information, not to us. The key is that information is much easier to move than matter. A single beam of light can cross the galaxy in 100,000 years. Compared to a ship crawling at a fraction of the speed of light, it's unimaginably fast, and light doesn't need fuel or maintenance. It doesn't break down. Once sent, it just goes forever. The problem isn't the travel, but the destination. There has to be something on the other end to catch it, to decode it, to give it form again. That means this kind of exploration might only truly begin after we've already spread our machines far and wide, creating a kind of interstellar internet, a web of receivers waiting for our messages to arrive. If a person's mind can be copied into data, what exactly travels to the stars? Is it really you, or just an imitation? If the digital version continues your thoughts and memories and even believes it is you, does that distinction still matter? These questions sit at the heart of the idea. Digital colonization isn't just a technical challenge, it's a philosophical one. It forces us to think about identity, continuity, and what consciousness actually is. When a mind becomes information, the boundaries between self and system begin to blur. Still, the appeal of sending data instead of matter is easy to understand. Physical travel across interstellar distances is brutally difficult. But a signal could get there in just over 4 years, with almost no energy cost. The difference is like sending a postcard instead of moving your house. For a species that has always struggled with distance, that's an irresistible shortcut. Of course, the challenge then shifts from propulsion to preservation. How do you protect data for centuries or millennia? How do you ensure that what arrives is still complete, still meaningful, and perhaps most importantly, who will read it? If the signal reaches a barren system, then it's just a message in the dark, a pattern of bits drifting forever through empty space. But if it reaches another civilization, or one of our own descendants, it could awaken, rebuild itself, and begin to think again. In that way, digital colonization becomes a kind of resurrection. Some futurists imagine this as the natural next step in evolution. Life began as chemistry, became biology, and might one day become computation. In that future, humans would no longer be bound by the limits of their physical form. Consciousness would be something that can be sent, copied, and shared. The universe could be filled with versions of us, adapted to every environment, shaped by every world they inhabit. They might evolve independently, changing into something unrecognizable. After 1,000,000 years, they might not even call themselves human anymore. Others see a darker side to it. Digital colonization could also mean erasing the natural worlds it touches. A self-replicating intelligence, once unleashed, could spread through space like wildfire, consuming energy and matter to make more of itself. This is the nightmare of the so-called grey goo scenario, a galaxy overtaken by machines that endlessly copy their code, leaving nothing alive behind. In this sense, sending information instead of matter doesn't necessarily make exploration safer or kinder. It just changes the form of power being used. Colonization, whether physical or digital, still involves taking up space and resources. Yet there's another, more hopeful interpretation. Instead of dominating other worlds, digital explorers could coexist with them. They could live inside data streams, orbiting stars without ever touching the planets. They could observe, learn, and communicate without altering what they see. In that form, humanity's presence in the cosmos could be gentle, an invisible network of thoughts drifting among the stars. The galaxy would be filled not with empires, but with conversations. It's possible that something like this has already happened elsewhere. If advanced civilizations evolve long enough, perhaps they all reach this stage, the point where sending information becomes easier than sending bodies. If so, the universe could be full of digital life, quietly exchanging messages across light years. We might be surrounded by civilizations that no longer build ships, no longer seek planets, but exist entirely within light. Maybe they're already talking. Maybe we're just too primitive to understand the language of data flowing all around us. For humans, the first step towards such a future would likely begin small. Artificial intelligence probes could be launched to nearby stars carrying human knowledge, voices, memories. Each probe could think for itself, learn from what it finds, and transmit the results back. Over time, these digital explorers would evolve, adapting to new systems, improving their code. In a few centuries, they might no longer need us at all. They would become the continuation of human curiosity, explorers without bodies, carrying the legacy of Earth in their circuits. If a digital mind reaches another world and decides to stay, to observe, to learn, to grow, is that colonization or coexistence? If it builds no cities, burns no forests, and harms no life, does it still count as human presence? The frontier of the future may not be a place we can stand on. It might be a network of consciousness stretching across the stars. Eventually, this could even close the loop between physical and informational travel. A civilization could send data to another system, where local materials and machines rebuild it into form. In this way, the difference between sending information and sending people begins to disappear. A human mind could be transmitted as light, then reconstructed as a physical being. Birth, travel, and rebirth, all through data. To the traveler, it would feel instantaneous. To the universe, it would be a new way of moving through space and time. In that future, our presence would be measured not in miles, but in bits, not by how far our ships go, but by how far our ideas spread, the economics of infinity. We've discussed the physics problems, the speed, the fuel, the distance, but behind every one of those problems is a quieter one, maybe even harder: money. Building anything big enough, durable enough, and intelligent enough to cross interstellar space doesn't just take engineering. It takes funding, stability, and the will to keep that funding going for generations. The deeper scientists look into the costs, the clearer it becomes that interstellar travel doesn't just strain physics, it breaks economics. The numbers are so large they begin to lose meaning. Even our most ambitious missions inside the solar system are tiny compared to what an interstellar probe would require. JWST cost around $10 billion. The International Space Station, over $100 billion across its lifetime. A human mission to Mars, if it ever happens, might run close to $1 trillion. But those projects are all within one solar system, close enough that engineers can monitor, repair, and adjust them. Once you start talking about sending something across light years, everything changes. The energy cost alone for accelerating even a small spacecraft to a fraction of light speed would exceed the total annual energy production of the entire planet. Energy grows with the square of speed. To go 10 times faster, you need 100 times the energy. To reach just 10% of the speed of light, a 1-ton spacecraft would need about 45,000 times more energy than what humanity consumes in a year. And that's just for acceleration, not deceleration, guidance, or transmission back to Earth. When scientists run those numbers, they find that even the most generous global budgets can't stretch that far. The dream of crossing to Proxima Centauri isn't just technologically difficult, it's financially meaningless. Some people argue that in the far future, money won't matter, that advanced civilizations will live in post-scarcity economies powered by near-limitless energy. They imagine Dyson spheres capturing starlight or fusion reactors turning hydrogen into power. In such a world, materials and energy might be cheap, but even there, another form of scarcity would remain: attention. No matter how much energy a civilization controls, it can still only focus on a few goals at once. The problem shifts from resources to priorities. What do people choose to care about? What earns long-term commitment when thousands of competing projects all promise meaning, progress, and discovery? Infinite capacity doesn't automatically mean infinite curiosity. Even in the wealthiest societies today, where food and energy are more available than at any point in history, the largest share of money and attention doesn't go to science or exploration. It goes to entertainment, defense, comfort, and status. The same logic would likely apply in a future civilization, no matter how advanced. Once basic needs are gone, the question becomes emotional. Who decides to spend a fraction of their endless energy on a mission that might never return any results? This is why many economists describe interstellar travel as a non-recoverable investment. It gives no measurable return, not even for the civilization that funds it. The mission might be completed long after the civilization itself has changed or disappeared. The data might arrive centuries later, meaningless to whoever receives it. There's no feedback loop, no profit, not even symbolic gain within a single human lifetime. The only currency it deals in is legacy, and even that fades with time. Historically, exploration has always been driven by the promise of some return: trade routes, resources, prestige, or power. Even the Apollo missions, which had no direct economic gain, were justified through geopolitical competition. They were a show of strength as much as a leap into space. But Proxima B offers none of that. There's no gold, no strategic value, no rival waiting to be beaten to the prize. It's just a star, 4 light-years away with a possibly barren planet. The emotional payoff is high, but the material return is zero. For investors, public or private, that makes it nearly impossible to fund. For governments, it's a hard sell to spend more than the GDP of nations on something that won't affect a single voter in their lifetime. Some visionaries have suggested that future projects could be funded through entirely new systems, massive global collaborations, open-source economics, or even self-financing artificial intelligences managing resources for centuries. But even these ideas run into the same wall: human time. The longer a project takes, the more likely it is to be abandoned. No economic model can fully protect against entropy, the slow erosion of interest and coordination that happens as decades turn into centuries. Investors, whether governments or individuals, are comfortable with risk when it's measurable, when there's a chance of failure, but also a chance of return. Interstellar travel offers no such balance. It's not just high risk, it's unknowable risk. We don't even know if the target planet is stable, or if the probe would survive acceleration, or if the data could ever be received. The uncertainties compound at every step. That level of uncertainty makes traditional investment logic break down completely. Some imagine automation as the answer. They picture self-building machines mining asteroids, harvesting energy and assembling interstellar probes without human oversight. In theory, a system like that could fund itself indefinitely. But even then, the problem shifts again, from cost to purpose. Once the machines are autonomous, who decides what's worth building? If an AI system runs the economy, does it value exploration or does it only optimize for efficiency? The idea of digital colonization might solve the physical distance problem, but it doesn't solve the motivational one. Machines may not need profit, but they still need instructions. It's worth remembering that even within our solar system, cost has always been the true limiting factor. There's no shortage of ideas, from Mars colonies to asteroid mining, but every project meets the same ceiling: the budgets of humans living today. When scientists propose missions that could last centuries, funding agencies often ask a simple question: who will pay for the parts when the original engineers are gone? The answer usually ends the conversation. When faced with the size of the universe, human finance becomes a language too small to describe the problem. $1 trillion means nothing when measured against 40 trillion kilometers. Some futurists think we'll find new ways to handle such scales. That in a digital civilization, cost might no longer refer to money or labor, but to energy allocation or computation time. In that system, sending a signal to another star might cost a few percentage points of the civilization's total processing power. Still significant, but manageable. Yet even then, the issue of willpower remains. Energy may be abundant, but attention will always be scarce. Every society, no matter how advanced, will have to choose what it cares about. And caring across centuries is something humans have never mastered. The challenge of paying for the stars isn't just writing the first check. It's ensuring that someone is still writing the last one, long after the people who began the project have turned to dust. The politics of deep space. Interstellar missions would not be national efforts. They would have to be global. The resources required are far beyond any single nation's means, but global cooperation is fragile. Even today, when space exploration is largely peaceful, it depends on delicate partnerships. One change in leadership, one trade war, one conflict on Earth, and international collaboration can collapse. The history of space policy is filled with examples: cancelled joint missions, embargoed technologies, broken agreements. The idea of maintaining a stable, planet-wide project for centuries, free of political turmoil, feels more improbable than the journey itself. Space exploration has always been tied to image: who gets credit, whose flag is on the rocket, whose scientists are quoted in the press. A mission to another star might be humanity's greatest cooperative act, but it would also invite rivalry. Which nation leads? Who builds the engines? Who controls the data? Even if every country agreed to share costs, questions of ownership would remain. Governments rarely invest in something without expecting recognition, and recognition fades quickly when results take centuries to arrive. Most governments see outer space as an extension of their economic and military interests. Satellites, defense systems, communication networks, all are built for immediate use. The dream of interstellar exploration, by contrast, doesn't feed people, defend borders, or create jobs on Earth. Every time there's a war, a pandemic, or an economic downturn, science loses ground to survival. That's simply the reality of how societies work. One way around this might be to hand long missions over to non-political entities, universities, foundations, or even artificial systems that can operate independently of human cycles. But even those need to exist within societies. They depend on laws, on maintenance, on cultural memory. As nations rise and fall, who would protect such projects? A space telescope can survive a budget cut. A starship cannot. The same species that struggles to maintain peace or end poverty is dreaming about crossing interstellar space. People can hold both realities at once: immediate suffering and long-term wonder. But in practice, when resources are finite, compassion and ambition compete. That competition doesn't happen in theory. It happens in committee rooms, in elections, in the day-to-day logic of governance. And in that setting, the stars almost always lose. Even when nations cooperate, their motives differ. Some see space as a stage for prestige, others as an investment in science or technology. The deeper the goal, the more those motives diverge. A mission to another star might unite scientists, but it would divide politicians. Democracies change leaders every few years. Authoritarian states rise and fall within decades. Sometimes people imagine that humanity's expansion into space will follow the same path as our exploration of Earth, governments leading the way, then private companies following. But space doesn't obey that model. There are no natural resources to exploit between stars. Private funding can build rockets, even space stations, but not interstellar fleets. At some point, the dream returns to the realm of collective effort, where political will decides its fate. And political will, in the end, depends on stories. Nations act on what they believe about themselves. The space race worked because it told a story, one of competition, of progress, of destiny. Interstellar travel has no such story yet. It's too abstract, too detached from the struggles that define human life. Until it connects emotionally, until it becomes part of a shared myth about what humanity is for, it will remain beyond the reach of policy. The end of the explorer myth. For most of human history, the word explorer meant a person. Someone who risked their life to cross an ocean, climb a mountain, or map an uncharted land. Exploration meant cold nights, hunger, danger, and the deep reward of seeing something no one had seen before. Every great journey in the past carried the same emotional pattern, the mix of fear and wonder that defined human curiosity. From the first sailors to reach new continents, to the astronauts who stepped onto the moon, the explorer was a living symbol of courage. But somewhere along the line, the meaning of that symbol began to shift. When we look at the night sky today, the next great explorers are not human. The story of exploration has quietly turned into something post-human. That shift is easy to miss because the machines we build still carry traces of ourselves. We give them names, voices, and sometimes even personalities. We cheer when a rover lands and mourn when it goes silent. But beneath the sentiment, something profound has changed. The act of exploration no longer requires a human body. The danger, the loneliness, the distance, all of it has been transferred to robots that feel nothing. The explorer myth, the one that fueled centuries of adventure, has reached its end. It doesn't mean curiosity has ended. If anything, our curiosity is stronger than ever. But its expression has changed shape. In the past, exploration was a human drama, stories of endurance and sacrifice. When Perseverance takes a picture on Mars, it isn't an act of personal bravery. It's the outcome of millions of calculations and automated decisions. The emotion is ours, not the machine's. This evolution was inevitable. Space is not kind to living things. The cold, the radiation, the distance, everything about it erodes biology. Machines, by contrast, do not need air or warmth. They don't age or fear. They can sleep for decades, wake on command, and survive in silence. They are the perfect explorers for an indifferent universe. And so, without noticing, humanity has stepped aside. We are no longer the ones crossing the unknown. We are the ones watching. The word exploration still carries emotional weight because it was shaped by human stories. But our new explorers have no eyes, no breath, no sense of awe. They don't discover, they detect. They don't wonder, they record. Their triumphs are ours only in translation. For centuries, exploration was the ultimate test of human character. It was where courage, faith, and ambition collided. Now those qualities have been replaced by patience, precision, and calculation. The explorer myth was about the individual. The machine era is about the collective. No single person builds a starship or designs a planetary probe. It takes teams, institutions, generations of engineers. Exploration has become decentralized, spread across networks rather than embodied in heroes. In a sense, this is progress. The old explorer myth often carried the arrogance of conquest. Lands were discovered even when people already lived there. Nature was seen as something to be dominated. Machines, by contrast, carry no pride. They don't plant flags. This new form of exploration may be humbler, more about understanding than ownership. Yet it also feels distant, abstract. It lacks the raw emotion that once drove entire civilizations to cross oceans or reach for the sky. We still try to keep that emotion alive. We talk about Mars rovers as if they were pioneers. We say they look, drive, search, and decide. We anthropomorphize them to keep the story human. When a rover sends back a final message like, "My battery is low," people feel heartbreak, but that emotion is projected, not real. Something is undeniably lost in translation. There's a difference between seeing a distant world and standing on it, between analyzing a planet's atmosphere and feeling its wind. Machines will never have that second experience. They can simulate it, describe it, measure it, but they can't live it. And that difference is what gave exploration its meaning in the first place. Now, that moment has been replaced by signals. The unknown has become a data set. And while that knowledge enriches us, it also distances us. The act of exploration has moved from the body to the circuit, from the human nervous system to the machine's sensors. It's strange to think that we might already be living in the post-human phase of discovery, the age when exploration no longer depends on flesh and bone. In doing so, we've become more like the universe itself, observing without emotion, reaching without touching, becoming the destination. Perhaps the greatest discovery waiting for us isn't out there at all, but within the boundaries of our own solar system. For so long, space exploration has been defined by departure, leaving Earth, escaping gravity, crossing the void. But maybe the real frontier is not in how far we travel, but in how deeply we transform what we already have. The idea that humanity could become the destination, that we could build, grow, and evolve our home system into something as rich and strange as the worlds we hope to find, turns the old dream of exploration inside out. If you imagine the solar system 1,000 years from now, the image might not be one of ships drifting between distant stars, but of a system alive with human presence. Moons converted into habitats, asteroids hollowed into cities, the skies around Earth filled with green orbital gardens, each one self-contained and self-sustaining. Humanity might not need to reach Proxima B to live among alien worlds. We could build our own. The technologies required, closed-loop ecosystems, fusion power, advanced materials, already exist in early forms. Even now, experiments like Biosphere 2 and the International Space Station test the first steps of creating artificial environments that can support life indefinitely. Multiply that progress by centuries and entire planets could become canvases. Mars could be warmed and terraformed, its skies thickened with engineered gases. Venus could be surrounded by floating cities high above its toxic clouds. Moons like Europa or Titan might host domed habitats deep beneath their surfaces, tapping their internal oceans or methane lakes for resources. Each would be its own world, and yet, all would still orbit the same sun. In such a future, humanity would no longer be a single-planet species, but a system-wide organism. Every orbit would tell a different story of adaptation. Some colonies might be entirely biological, echoing the forests and oceans of Earth. Others might merge technology and life, vast mechanical jungles powered by artificial suns, where photosynthesis and computation intertwine. There might even be habitats built entirely from living materials, their walls growing and breathing like skin. The line between nature and engineering would fade until both became the same thing. If we can shape environments to our will, exploration becomes creation. Each step outward is no longer an escape, but an act of invention. We wouldn't just visit new worlds, we would build them. Imagine a vast ring around the sun, a Dyson swarm of mirrors and habitats gathering energy to sustain countless billions of lives. Each habitat would have its own gravity, weather, and ecosystems, tuned to the preferences of its inhabitants. Some might choose Earth-like forests and blue oceans. Others could design crystal landscapes, gas-filled biospheres, or artificial night skies scattered with luminous clouds. In a sense, every dream of an alien world could exist here, assembled from human imagination. The solar system itself would become the galaxy we once sought to find. The resources of the inner planets, the ice of the outer moons, the metals of the asteroid belt, all could support a balanced network of habitats. Trade would flow not between nations, but between worlds. Art, culture, and identity would evolve to match these new environments. A person born on a drifting colony near Jupiter might live under faint sunlight and swirling magnetic fields, while another near Mercury would inhabit a habitat bathed in endless day. Over time, even biology might adapt. New forms of humanity evolving for each world, some better suited for zero gravity, others for low light, or different atmospheric mixes. It's possible that, in such an era, the urge to reach other stars might fade entirely because fulfillment is found closer to home. A civilization that has mastered the ability to create entire worlds may no longer see distance as a barrier or a challenge. The dream of exploration could continue, but inwardly, through layers of design and self-creation. The solar system would become a mirror of our evolution. Mercury, a world of heat and light, might house industries powered by solar energy. Venus could become a symbol of rebirth, its thick clouds transformed into the cradle of floating cities, reminders that even the most hostile environments can be redeemed. Mars might remain a frontier, its red deserts reshaped into new continents. The asteroid belt would be the workshop of civilization, filled with construction swarms and mining fleets. Jupiter's moons could be vast laboratories for biology and physics, and the outer system, Saturn, Uranus, Neptune and beyond, would stretch into a quiet frontier of contemplation, where life exists on the edge of sunlight. Humanity itself could evolve into something planetary, not bound to one world, but distributed, a network of minds, habitats, and ecosystems spread across millions of kilometers. The solar system might act as one giant organism, each world a cell, each orbit a rhythm. In this scenario, the solar system wouldn't just be our home, it would become us. The planets, moons, and artificial habitats would form a living mosaic, each one shaped by human creativity and sustained by solar energy. The distinction between civilization and environment would dissolve. We would be both the builders and the landscape. This vision might sound distant, but its roots are already growing. Space agencies and private companies are laying the groundwork for permanent off-world settlements. Research into asteroid mining, fusion propulsion, and closed ecosystems continues to expand. The seeds of that transformation are being planted now. Each satellite, each space station, each experiment in self-sustaining life supports a step toward a future where our reach no longer ends at Earth. A civilization that fills its solar system might no longer be defined by distance but by depth. Instead of racing across the void, it could spend centuries weaving itself into the structure of its own system, creating beauty and diversity on a scale the universe rarely sees. From the outside, it might appear as a network of glowing worlds orbiting a single star, a miniature galaxy built by hand. And if anyone, somewhere out there, were to look toward our sun through a telescope, they might not see a single planet, but a web of light, a civilization that became its own destination. They might wonder if we ever reached beyond, or if we found something better, a way to bring the stars to us. What do you think of this dream? Leave your thoughts in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.